figure out if we can leverage the in-context learning ability of the vision language models to actually adapt to this particular situation and leverage history in order to actually be able to try something different compared to what it's been tried before. And even though it actually can't see that its shoulder is stuck here, it should be able to know from history that its current strategy isn't working and it might need to do something different. And so specifically what we're going to do is we're going to incorporate prior information from the history. So the vision language model won't just take as input the current image, but it'll also take as input a context that includes everything that it was doing previously. And we're also going to have the vision language model output a multi-step plan rather than just predict one skill for the current time step. And this allows it to kind of not be too greedy in taking actions and kind of foresee potential failures into the future. This is a lot like model predictive control, except at a high level. And so we'll refer to this approach as vision language model predictive control, or VLADR. We looked at 5 different challenging settings in the real world with unseen obstacles, only egocentric perception. The robot isn't trained on any of these scenes. It's just using the vision language model out of the box to adaptively handle these kinds of situations. Yeah. And so we can go back to our end couch example where the VLM on its own was kind of struggling to perform the task. And what we find is when you include history and multi-step planning, it's able to quickly figure out that the couch is a dead end and go around it, eventually climb over this other obstacle in order to reach the goal. We also looked at a number of other examples. Here's one more qualitative example where we see that the robot, without multi-step planning, ends up being a little bit kind of greedy in some ways and trying to kind of go through the bushes in different ways and is struggling to find the red shoe toy. And in contrast, with our approach, is able to kind of reason multiple steps into the future and kind of come up with a plan that explores and then eventually tries to find the shoe toy. Quantitatively, we found that incorporating history and multi-step planning leads to a 20% improvement, both in the average time and median time to complete the task, as well as the overall success rate. Both history and multi-step planning are quite helpful when using VLMs for high-level planning, essentially because this sort of reasoning over time really improves the resilience of the robot if it gets stuck. Cool. Yeah, so the takeaways here is that history and multi-step planning can improve the robot's adaptability and in turn improving its resilience and performance in a number of really challenging scenarios that involve both higher level reasoning and various low level primitives like crawling, climbing, walking, moving backwards, and so forth. And the kind of approach of predicting multiple skills into the future and then executing the first one is analogous to model predictive control, but at a much higher level in the space of this vision language model planner. Cool, and then of course there's always lots of open questions as you complete a research project. And some big questions here is that we use a fairly simple approach to tie the language commands to the low-level primitives, where we just attached a verbal name to multiple different primitives that the controller can perform. But there's lots of different kind of room for improvement in terms of grounding language to be more expressive beyond just a set of like 7 skills and corresponding magnitudes. And there may also be scenarios where you want to expand on the language abstraction rather than only using language to describe the low-level skills. Cool. So to summarize, I talked about a few different ways that language can help reasoning and performance in robots. Specifically, we found that powerful vision language models substantially aided robot generalization through a new open source vision language action model. We found that we can interactively correct and improve robots just with verbal feedback without additional demonstration data. And we also found that VLMs can actually plan adaptively using in-context learning for greater resilience. I should also, of course, highlight that robot data also plays a really important role. Language doesn't solve a lot of things by itself, and we saw that theme a couple times in the work. For example, when we were looking at the language corrections, the low level policy kind of still remained a bottleneck for good performance, and improving that would improve the overall system. Great. I'd like to end there. I'd like to especially highlight the students who led the work. Mujan, Carl, and Sid led the open VLA work. Andy, Alec, Andy, and Govind led the last work on locomotion, and Lucy led the language correction work in the middle. Great, and I think we also have some time for questions.
So Chelsea can hear us from here?
Yeah, I can hear you.
Okay, sounds great. So I guess we have time for 3 questions. If you have any questions, please raise your hand or directly come to the microphone. Any questions? So Chelsea, I would like to ask the questions regarding how we develop the language model and robotics together. So I'm just curious, what's your opinion of like when we develop the language models, should we include the robotics data when we pre-train, for example, a language model, or we should first train a language model and then fine-tune our robotics data? And what do you see the options here?
Yeah, I think that's a great question. I think that generally vision language models oftentimes aren't necessarily developed with robotics applications in mind. They're developed more for like chat applications or video analysis or even like web agents or something like that. And as a result, in the OpenVLA work, we actually found that we did a little kind of benchmark of VLMs on our robot data, and we found that a lot of the open source models actually really struggled to even do kind of fairly basic functionality for on our robot data. We found that Lava and Prismatic at the time were some of the strongest at being able to identify objects in the robot scenes. So generally, because there's a lot of room for improvement on open source vision language models, I also think that in the long run, it absolutely makes sense for them to incorporate robot data into training. I think that right now, a lot of the robot data sets that we have are not that mature. They're kind of aggregated. We've come a long way. We actually are starting to have large data sets in robotics for the first time, which is really amazing. But there's also really, they're kind of not nearly as mature. It's kind of like it was like the first time that like, I don't know, ImageNet or something, maybe not even ImageNet was introduced into the computer vision field. There's always kind of issues with the data set. I mentioned some curation things that we did in OpenVLA. And so, yeah, there's a lot of room for improvement on the robot data sets, and that would also it'd be important to be careful of that when training vision language models.
Yeah, question? Yeah, sure. Hi. So, language is a great medium of communication when it comes to human communication. But communicating with machines may be more efficiently done with non-language means also. So for instance, you give examples of correcting the robot behavior, and I work on HoloLens, and many times even for humans, it's better to give instruction in situ with respect to the scene that it's this knob, not that knob, instead of language instructions. And similarly, in robots also communication can happen via images, via schematics, and so on. Have you done any work on that, or any thoughts on that?
Yeah, definitely. So I do think that language remains very easy for humans, but it's not always the easiest for robots to interpret. And there's also sometimes we might want to provide more expressive forms of information than what is easy to provide in language. And we had one work, I don't have slides on it up right now, but we have had one work where instead of just conditioning on language, we also conditioned on like just like a hand-drawn trajectory on the image of where a robot should move. And we call that this work with RT trajectory. And so, yeah, we've definitely looked at other ways in which you can provide information to robots. And I think that exploring those other modalities is quite valuable. And yeah, definitely worth doing more of. And I think that actually, in many ways, if you go back to the EA robot work, this sort of approach is, we kind of developed it for language, but you can really replace this high-level policy and the supervision you're providing here with many other things, provide intervention in many other modalities, such as trajectory, such as pointing or whatever, as long as the low-level policy can interpret it. I think that this general paradigm is quite flexible, and yeah, it'd be really interesting to explore this kind of method with other mediums of communication here. Yeah.
Hello, hi. Hello?
Hello?
Anything else?
Hello?
Yeah, I can hear you.
Hello, hi. Hi, Jensen. Thanks for the presentation. I have a quick question about the language. You can use language for a lot of things like communication and planning. But however, we also know like language often have this issue of hallucination, like especially for high-level planning. Sometimes it gives some like planning instructions which is weird or wrong, or like how do you see this problem? And if so, how do you solve this problem?
And so the question was like, how do you address, have you seen hallucinations and how do you address it? Is that the problem?
Yes.
Yeah, so let's see. I think the term hallucination generally, it can refer to a lot of different things potentially. In this project, actually, we did try using a vision language model as the high-level policy, and we found that it was struggling to interpret the images from this robot and consistently provide correct language commands. And so I think that for those sorts of things, these images might just be out of distribution compared to what the robot compared to what the vision language model is used to seeing. And fine-tuning is a really natural remedy for that. So that's definitely one thing. With regard to the last project where we were using a vision language model to high-level plan for locomotion, we also in some ways, I guess we may have seen what you could call hallucination in this work as well. We did a fair amount of work to iterate on the prompt that's used for the language model, and we included the full prompt in the paper. So that I think can be somewhat helpful. And then definitely like incorporating history and incorporating multi-step planning. At least in our experiments, found that it led to a more performant language model. And in some ways you could think of that as reducing hallucinations.
Thank you for the talk. I have questions regarding your learning strategy. You mentioned you learned for 15 days. Why did you stop in 15 days? And what happens if you learn more?
Yeah, that's a great question. We stopped at 15 days because that was the budget that we had. And I think that it's very possible that it might have gotten better with more training. So if anyone wants to donate some compute for this project, we would definitely take it. Yeah, and we actually, one other note here is there was actually one data set that we included on the first part of training, and then we found that the model was generally like training pretty slowly on that data set, and so we actually excluded it for the second week of training because we felt like it might spend a lot of capacity trying to learn that data set when we wanted to make sure that it was performing well on the other data sets, which were also like better representative of the data sets that prior works had trained on and the robots that have been considered in prior evaluations and in our evaluation. It does seem like these models tend to train quite slowly, and also that and also that there's room for improvement in terms of like we could add even more data to this that we have. So I think that there's definitely a lot of research to be done to figure out if there's ways to accelerate trading. One thing that we found that actually I think I forgot to mention is that we actually tried freezing the vision encoder because there's a lot of works on the VLADR side that have found that you can do that quite successfully. But we found that it was actually really important to fine tune everything end to end, at least at the beginning of training, or at least for some parts of training. But it could be interesting to explore something where you fine tune everything end to end to start, and then and then from there maybe you kind of selectively fine tune other parts of the model just to make fine tuning faster. Yeah, so lots of experiments that could be done here. Compute is definitely the limitation that we've had in the when doing this in a more academic space.
Let's do one more very quick question, and then we have to.
Yeah, hi. I was wondering, you mentioned that your model did better than RT2X, despite being much smaller. Can you elaborate a bit more on why you think that's the case and what you learned from that? Like you said, data curation, maybe some learnings going forward.
Yeah, so it's because of the compute limitations, like we weren't able to do like another 15-day run that avoided some of these choices, unfortunately. So we can't really be certain about what's causing the improvement compared to these three things. But the three key differences are that I mean, obviously the pre-trained model is different. I would I think that Palm, well, so we're using Llama 2, but I think it's probably weaker language models in Palm. So probably if anything on the architectural side is improving it, to the encoders, we're using Sigma and 9OV2 instead of the PolyX encoder. And then if there's anything on the data side that we're improving it, that we're using more data, and this curation thing that I mentioned. Specifically, the curation that we did is for one of the data sets, it's somewhat known to have kind of zero actions in a small portion of the data set, especially at the beginning and end of episodes, and we removed data with zero actions from the data set. But yeah, unfortunately, it's hard to get a complete answer without more compute to run like a really head-to-head comparison without some of these choices.
Yeah, I think we are running out of time, and let's thank our speaker, Professor Chelsea Fei again, and thank you so much for this wonderful talk. Our interest here, and we're looking forward to seeing where the objects are. I don't understand what they're looking to say, but the visual engagement means that we do that action. In this course, and that's the yeah, yes, that's what we learned. For the thing it takes, you could say, let's say this far away from where you are, you have an obstacle. Now, whether it understands what it actually is, or whether it just understands it's an obstacle, I don't know the details, but that's what the vision VLADR is. Think of it like the GPT with text, it's just text. Now you could add like a picture of a house, and it would know it's a house. You don't have to say it. That's what the vision language model is, and she's using that and adding actions to it. So therefore, you can then predict. If I see a house, don't walk there, go around.
All right. I hope so. Maybe somebody can check the Zoom if one of the organizers can do that, because I think it's working. But it's always good to check. It's great to be here and great to talk about vision and language for robotics and for autonomous driving. Although I think I'm mostly going to be talking about robotics in that direction. And it's cool that there's a workshop on this. I think, and it's probably almost mainstream. I think, years ago, it would be controversial to say that you would want to have language for autonomous driving or robotics, or that it might be a thing. But I hope by the end of this talk, I'll convince you that it's a great idea, or there's a lot of interesting stuff going on. And I'm going to end up with full robotics demos, and I'll end up with some models that actually have no language in them. They're just robotic transformers, and I'll end up with actually I'm gonna show you the first release of our new model based on large multimodal models based on lava that is fully fine-tuned to do robotic action as well. We call it larva, lava to larva. So I'll get there at the end of this talk, but I'm going to start off, actually, if you don't mind, I'm going to have a little detour, a little bit of a philosophical detour and in fact, I have a weird title, and the title is Ungrounded Language Models for Perception and Robotics, right? Question mark at the end there. Because I'm actually interested to see, and I think the biggest change in my thinking, if my laptop will start to work, let's hope it works. The biggest change in my thinking, I used to think of these large language models as kind of being something else than I needed to worry about, especially like maybe 2 years ago. These LLMs were out there. They were really, they were doing great things with text, but they weren't grounded. And for a decade or 2 decades, or even more, I don't want to tell you how many decades I've been thinking about these things. I've always thought about vision and language models. I've always been interested in grounding. How do you figure out what things in the world correspond to what words or what utterances? And so grounding's always been an interesting focus for me. And a text-only model is ungrounded. How could a text-only model know the geometric relations of things in the world? It just can't happen, right? Can't happen. So the LLMs are amazing at textual translation and reasoning. I've always thought they're a great place to define tasks. And that's why I've been a vision person who's very interested in language for several decades. I don't like just having category number 5 and category number 27. I want to have a little natural language string describing the category so a human can talk about it. But I wouldn't have been fooled a few years ago into thinking that LLMs alone, something that's only ever seen text, is grounded in the real world, right? And there's this in the last 5 or 7 years, there's been the stochastic parrot debates. In earlier generations, that debate was often called the Chinese room argument. I'm sure most of you have heard of that. But I'd say in the last 2 years, my own belief in these issues has really been thrown upside down, or jumbled up at least. And I'll show you some of the work in the next 10 or 15 minutes that's led to that realization. And I'm going to start off actually talking about something that has nothing to do with autonomous driving or robotics, but actually multimodal language parsing. And this was the first work where I sort of had my eyes open, and this was about 2 years ago, where, wait a minute, a model that's never seen a pixel actually understands spatial relationships in the real world? That doesn't make any sense to me. It didn't make any sense to me at the time. And the motivation is a couple of my students, I think, were really had looked over at the language community and seen the language community in 2019 to 2022 come to the same conclusion that I had always thought was true, which is, oh, you need pixels in order to understand the physical world in language. And there were a whole bunch of award-winning papers where basically people added visual features into unsupervised parsing and showed that it helped, which again, that was God's truth to me. I was definitely on board with that idea that, like, if you want to figure out how to parse a sentence, like a cat sipping from the cup on the table, or a cat is sitting under the table, or a dog, like, even parsing requires a little bit of understanding the scene in this case, because you want to know, is the cat on the table, or is the cup on the table? Are they both on the table? you know, the paradigm du jour up until, like, as I said, a year or two ago, is multimodality is the key to really understanding the physical world. You know, and looking at the pixels and having a data, you know, looking at the pixels at scale will help you learn these things. Well, I think my grad students had seen all the award-winning papers that had been just achieved, and also none of these models used LLM, so they thought they could crank out another award-winning paper of the same exact type. So that was going to be a lot of fun. So they went ahead and just, you know, took the latest and greatest vision features, and we expected to see a strong bump on top of what the prior you know, visual grounding features were. And the good news is we got a strong bump by adding those powerful text-only language model features, like I guess it was T5 or BERT style features back then. I can't remember exactly which. The bad news, for the purposes of the conventional view here, was that adding those LLMs actually destroyed all of the results of adding vision. So as soon as we added sufficiently powerful text-only features to that problem, there was no boost left by adding pixels in. At least the level of grounding that you need to solve this task, which admittedly is pretty weak. I mean, to do parsing, you only need really crude understanding of general spatial relations. I don't need to understand whether my left digit is, you know, what's the configuration of my hand or something like that. But anyway, that was the first signal I saw that, wait a minute, a model that's never seen a pixel knows that an airplane is potentially in the sky, or that boats are on the water, or that, you know, cats are a different size than an apple or something like that. So unfortunately, adding pixels back got us nothing. So we ended up, this was the first realization we had of maybe text-only models actually are grounded in a certain way. So this is the first thing I'm going to tell you about. There was that unsupervised parsing result, and I'm still going to be on the first bullet here for the next part of the talk. And we're going to see how actually not only unsupervised parsing, but also graphics. Text-only models can actually add a significant boost to stable diffusion class models. So again, a slight detour into graphics before I come back to robotics. Hope you'll indulge me. And these results are like about a year old, and at least 6 months ago, they were still very, very current. I don't want to say what Sora can do or what Sora can't do, but at least the first generation of these models really were very weak with regard to attribute binding and numeracy and things like that. So you'd say a gray cat and an orange dog in the grass. Wait, where's that orange dog? The orange ball is not an orange dog, right? If you would do spatial relations, these models would also not be so. And there's there's like dozens of papers, probably even at this conference, explaining why this is true. Probably it's something to do with the underlying clip representation these early models had, so on and so forth. But what was really interesting is we found actually that text-only models, so this is a stable diffusion model, you're all probably familiar with it, but what was surprising to us is that a very, very simple idea, which was to ask a text-only model what should have been in the scene and what the spatial layout should have been in the scene, so significantly ameliorated this problem. So again, the models can't do negation. And the one that I loved back when, you know, about a year ago, pretty much every model failed on this. If you asked it to render a man in red and a woman in blue, you would not get it. These models just did not want to dress a man in red when they had an opportunity to dress a woman in red. Again, I think the latest models don't do this, but maybe they've seen my talk from before. But surprisingly, text-only models had no trouble, right? If you actually, and this was the archive we had a year-ish ago, and there's actually a series of 3 papers here. I'm not going to go over all of them. If you're interested in this work, definitely find the whole chain. We first do it for images, then we do it for video, and then we do it interactively. But just the core of the idea is present on this slide, which is a text-only LLM gives you a coarse layout. If I tell you a realistic photo of a gray cat and an orange dog on the grass, and I give you a little bit of prompting about how a text-only model can generate box layouts just by, you know, expressing the coordinates of the bounding boxes in text, the model can say, hey, here's a pretty good layout for what the scene should look like. And that can condition the diffusion model. and fix this problem that it had, at least the version of diffusion models that were prevalent. Even production models that were prevalent a year ago had these kinds of problems. And without any fine tuning, this was done in like a week on like academic compute. This connection of these two models saying, let's take the strength of a text-only model that, even though it's never seen a pixel, knows more about scene grounding than the state-of-the-art production stable diffusion models like last year. That surprised me, but it worked really well. And so we basically concatenated an LLM and stable diffusion, asked the LLM to basically tell us what should be in the scene in crude strokes, and it would be able to render these scene layouts. And then these scene layouts could condition stable diffusion. And there's a variety of different ways you can do that. There's one of them that's in our paper. And there's actually a couple others even from my own group. I won't go into that right now, but just many of you are probably aware that you can basically constrain the cross attention in a diffusion model to respect certain geometric regions and enforce that certain constraints or attributes attached to each of those, and then basically back that out and re-render a new image where you do have a box that essentially has a gray cat in it and another box that essentially has you can get the man dressed in red and the woman dressed in blue, and spatial relations and numeracy. And again, if you want to go through it, or if I end up finishing early, I can probably go back and show you some examples where we render videos. Now, they don't look as good as Sora, but right before Sora came out, they looked really good. And we have interactive versions. So maybe we don't just start from the LLM, we start from an image and have actually a LMM that looks at the image, comes up with initial parsing, can refine it, and so on and so forth. So it's exciting to see, to me, what text-only language models know about the visual world. And at least the vignettes that I've just shown you suggest to me that perceptual semantics for parsing, scene layouts for static rendering, motion graphs for video generation. I didn't show you that, but trust me, it's there. And last but not least, even human pose. Like, I would normally, as a vision person, think that human pose estimation is probably the most vision person's vision problem. I mean, you don't know language that's going to help you there, right? But wait, there's more. Actually, if you think about it, the hardest part, I think, about pose right now is getting a great pose prior. Where do we get all that data to learn human pose from? And there are many labs around the world which have their scanning setups, and many people are trying to collect images of people walking on YouTube. But it's still a pretty big challenge of understanding all of the nuances of human pose. For example, when a bride and groom walk down the aisle, they usually hold hands, and holding hands is a certain kind of thing. Where do we get that prior? I mean, we're going to set up a motion capture apparatus in churches and collect 1,000 examples of people. I mean, why is it that we just know that that's true? Well, we know that it's true because there's hundreds of stories or thousands of stories, or I don't know how many stories, but there's actually a lot of text on the internet. Certainly large multimodal language models. I guess we can debate. You can read our paper to see what our claim exactly on, is this a text-only phenomena or is it a multimodal phenomena? But you'll certainly agree that large multimodal text models that have looked throughout the world actually know a lot about the spatial relationships and involved in human pose. For example, that in a certain kind of embrace, you'll be arm in arm, or that a yoga pose might have a certain kind of characteristic, or at least there's going to be manuals written on the web of all sorts of interactions. So that's one of our latest works, where we basically go out and use a large multimodal model, or to some degree, even just a large language model. But I think the best version of this idea is one where the large multimodal model also looks at the overall gist of the scene and says, it looks like this is a bride and groom, and it looks like they're holding hands. So I probably think they're holding hands because that's what my language prior tells me is most likely in this case. And then the language model can generate a series of constraints that a vision model can go in and try and impose when actually solving for a full optimization. If you're interested in that, we had an archive on that last month. And we called it pose priors from language models. So I think I've started in text only land, and I'm moving towards robotics. But I'm excited. It's crazy to me to see how much text only LLMs can actually see about the world. But But as we think about the utility of these language models for autonomous driving and robotics, which is of course the theme of this workshop, we immediately start moving to multimodal models. And I'm mostly going to talk about the open source multimodal models, just because those are the ones that are most fun for academics to work on. But of course, there are, I'm not going to do the full literature of Flamingo and Palm and whatnot. But even models like Lava, which are based on Llama, have recently, as everyone in this room is probably aware, been trained to look at pixels and jointly process images and language so that you can ask questions about an image. And I think it's rather exciting in the last year to see now not only can you build these models that can take text and image as input, but they can take that and they can output text, or they can also output references. I'm not going to talk about full image generation, but even simple, relatively simple models that don't require a tremendous amount of, boil the ocean class compute can be added to this Lava class model. Here, a model called Lisa. Unfortunately, I don't have the site on the slide. That's not our work. Adds a SAM decoder to the Lava model and can not just output text, but can basically output segments. If I want to say, where's the horse in the image, the LLM that's been trained in this way, it can say, oh, there is a horse in the image, and here it is. Actually, we have an extension to that work that we call Sesame that is presented at this conference that deals with a limitation in that class of models. The prior models kind of over-indexed on this segmentation task, and they lost the underlying ability to tell you, actually, there is no horse in the image, or if I ask for a bowl of pineapples in this image, the model would actually randomly find the closest thing in the image. It's sort of like the forced choice scenario in segmentation. And we extended the model, as we called it, Sesame, to have a conversational interface and say, if the object is in the image, it'll point to it. If not, it'll tell you, wait a minute, that object isn't there. Where's the closest related object? Or actually, there's no object at all. Or did you mean something else? And of course, to build this model, we had to construct a relatively small new data set and benchmark. I don't think that's coming from this room, but if it is, please stop tapping the microphone. And if you're interested in this, you can see a poster at the main conference. And basically, it's just pushing the state of the art in these open models for referring to things in the image from a large multimodal model and doing so in a way that's conversational and still retains the ability to overcome what we call false premises. So here's an example where the model doesn't get confused when you ask for an object that's not in the scene and says, actually, there's no lion, so I'm not going to come up with a lion segment, but there is a giraffe. Maybe you wanted that, or maybe you didn't want anything at all, and I'm just not going to give you anything. So that's exciting. Not quite yet to robotics and autonomous driving. I'm going to also do a quick, and now I'm going to do a transition towards away from language just for a moment, and say maybe we don't need language. Let's actually explore models that are only vision, and then only robotics, and then we're going to come back to a model that actually combines all of them. So the larva model that I'm going to come back to at the end is in some sense extending this class of models that I just showed for segmentation. It was inspiring that we could build large multimodal models that could generate segments. Segments are just static sets of points at a moment in time. If you can imagine not just predicting a segment, but predicting a trajectory, or decoding a spatiotemporal trajectory, or a set of waypoints, it seems like there's a nice continuum there, and that's in fact what we did and applied it to large robotic data sets in the larva model. But to get there, I'm going to first tell you about our vision only models, and then our robotics only models, and then we'll get to larva. Because I think, you know, I am a vision person, and even though in practice there's no reason we can't pre-train on vision models, eventually it's nice to say, what could you do without language at all? So now I'm going to take the opposite stance from what I've had in the last few moments and say, it's exciting to think of, can we have a large model? Maybe even I would call, like a decade ago, I still would have called it a large language model. I would just say there's no text in this language. This is a language of visual tokens. Or in the robotics case, I still would want to call it a language model. It's just it's a language on robotic tokens. Outside this room, I won't use those terms because it confuses the lay public to try and say that there can be a language model without text. And maybe even half of you disagree with me. But here we have a large vision model, which is essentially a language model only on pixels. This is a work with several co-authors from Berkeley and elsewhere. Yu Tongbai led the project. I think her poster's on Friday for this, if you're interested. And she essentially went and trained a Llama class architecture just on pixels and on sequences of images, and showed that the scaling recipe that has proven the test of time in language also is proving effective in vision as well. And you know, it's basically pushing beyond the frontiers, the limits that we had reached, or the headroom, the ceiling that we had reached with MAE. And so we're just going to go beyond that. MAE, very high impact work. Everyone's probably aware of it. Trained on ImageNet, BERT style regression loss. And the language folks kind of, you know, were ahead of us on that. And basically tokenized, autoregressive, cross entropy, you know, classification loss are the bigger data. Those are the elements that seem to scale, and that's the key ingredient of the large vision model work. For data, Yutong collected basically just tokenized every image data set she could find, put it into a single unified setting. And we can debate whether it's supervised or unsupervised. You know, it's unsupervised in the same way that GPT pre-training is unsupervised, if you believe that's unsupervised. I mean, but is there some sort of signal in there? Like the data has examples of image and result in the data, or like, you know, when you train a GPT translation model, there's examples of English and French. That's supervision, but we often don't think of that as supervised in the same sense. So let's avoid that debate. I mean, there's a lot of cool stuff in here which is constructed to show vision tasks, and that's implicit in the sequence that I'll show you in a minute. And there's this notion of visual sentences. Let me try and zoom in here a little bit. Yeah, this is where you might think that there's some supervision in there, and I wouldn't argue with you, except to the degree that I just did. Take series of visual sentences, and these are going to be and the tokens therein. Each image, of course, is decoded into an array of VIT tokens. Other than that, there's no representation of pose or depth or whatnot, but there are images that might have graphics that are drawn on them that correspond to those things. And 400, sorry. Okay, bad news. Let me see if I can get back to where I was. Good. 420 billion tokens. Lots of implementation details. It does scale, and the loss goes down. And as the data increases, the performance on downstream tasks does increase. And again, this is vision only model. Again, I'm going to try and zoom in here so we can see some more stuff. So this is a visual sentence. This is essentially visual prompting to tell the model, I want to do pose estimation, because I'm showing you pairs of natural image and a pose graphic. And without ever knowing anything about pose, except for all the data that it's trained to reconstruct using next token prediction, it can generate the kind of output on the upper right. It can do edge detection. It can do depth estimation. It can do segmentation. It can do some sort of surface normal estimation, and even completion of different figures. Now, I mean, I don't know how impressed I am with that one because I'm sure the Kanitsa triangle is in the training set, but whatever. This is a problem with all of these kinds of models, and I think that's still an open problem. Just next frame prediction, I apologize for that. It can actually render, I'll just keep going, it can render key points in 3D. These are kind of cool. It has a certain degree of numeracy, but not perfect. And I wish I could just hit back and not go too far. Okay, now this one. That seems like okay, good. So the last but not least, here's some very, or second to last, and certainly not least, here's some interpolation of some graphics and some arrays and some cats. And I think these are pretty cool. The bottom one is not super realistic. I think this, as if you go to Yutong's poster, you can see the latest results. And this is not a final work in a large vision model, but I think this is almost one of the first proof of lives. This thing is actually working and has some interesting properties. It's able to solve some of these nonverbal IQ tasks, which is kind of cool. So that's exciting. All right, but this is a robotics and autonomous driving workshop, and I have 15 minutes left, so I gotta get back on the program here. And I want to now tell you about our work on large robotic models. The speaker following me, I'm actually going to announce a small edit to the schedule as the organizers told me. Actually, Jitendra was supposed to speak after me. I've heard he's been called away for a family issue. Ilya Radasovic is going to be able to actually stand in for him. And actually, these are Ilya's slides. So I'm going to give a preview of them, but you can come back at 11 to hear the full version of that talk, and Boyi can announce this in full detail. So there'll be some overlap here with some of these slides and what you may, I see Ilya walking in the back of the room right there. I just announced that you're giving a talk in 25 minutes, and that this is going to be a preview of some of your slides as well. So I've talked about language-only models. I've talked about how these models can become multimodal, generate segments, and refer to things. And we've just looked at large vision-only models. Now let's look at large robotic-only models. How can these, again, there'll be no text here. We'll come back to that at the very end with this larva model. But what's really exciting in the work that Ilya and others have been leading is the notion that even without text, these models can drive a significant amount of performance. And the key idea here is to think of this, and starting with the work that was at Coral in 23 on sensory motor pre-training, is to think of it as sort of the language of the physical world, right? Where we have a sequence of tokens, and we're going to model those with a quote unquote language model. Again, a language model that's not looking at text. It has no text and has never seen text in this case, but predict the future, right? So we take the tokenized world. Some of the results I'll show you will have cameras and some of them won't. But either way, it's still the same paradigm. I'm going to have a transformer that's going to be observing a sequence of tokens that include sensory observations, proprioceptive observations, a motor action, and a sort of and the resulting proprioceptive state of the action of the agent, and these models can be trained on a corpus of data and then fine-tuned on downstream tasks. And maybe Ilya will have a few more examples, so I won't go through all of them. I'll just keep showing the highlights of this. Not only is this paradigm applicable, and have we been developing it in the lab at Berkeley for manipulation, both single arm manipulation and dual arm manipulation, but a very exciting platform in robotics is legged locomotion and humanoid locomotion. And I think it's really cool to see that these models are also working in that context. And the same policy the same paradigm and ultimately similar policies plays out. And in the most mature version of this work, again, if you want all the details, stay for Ilya's longer version of this talk in the next hour. We train it as a next token prediction problem using sets of data that are collected from different sources, including a neural network policy, a model-based controller, a motion capture rig, and internet videos. I'll tease a few examples of that in the following slide. And again, learn a transformer that takes these models as these tokenized data samples as input and learns to predict it and reconstruct it, and basically sees all the observations and outputs a token corresponding to a motor control command, and that generates an action for the robot in the real world, and that we will see the robot working in certain videos in the following slides. And this is a paradigm that's able to handle missing data naturally, as multimodal transformer architectures have been doing in other domains and are able to do here. So for many of the data sources that we have, if not most of them, we won't have access to action tokens. Yet we want to train our model with action tokens, and that can be naturally accomplished by just masking the action token and not putting a loss on its generation while we train a transformer on the data without action. We don't have to impute actions and then train that. But when we do have complete data, such as prior walking sequences from our robot or from the model-based controller and simulation, or the neural net controller and simulation, we can train on those. Okay, sorry, oops, back one. So here are as I mentioned, the different sources of training for these walking trajectories, and the neural net controller has both actions and observations. The model-based controller, actually, I spoke a minute ago, does not actually give us actions. It only gives us observations, as does the mocap and the internet videos. I think the most exciting, maybe scalable path in the future is actually just watching people walk in the real world together. There's a lot of motion capture data ready to be scraped now that the state of the art of models that can track human pose are getting good enough. These all generate the tokens that our model ends up using to predict how it walks in San Francisco. Ilya will be talking next, and he'll show you even more eye candy. It walks in San Francisco. It actually walks in the steepest hill in San Francisco. I was actually there helping, watching the data collection. And it's really interesting to see how kids and animals in actually kids seem to like the robot. Animals are scared of the robot. It's very interesting. So we have an archive out in the last few months if you're interested in this, and you can see Ilya's talk. And in the last few minutes, I'm excited about all these results, and I want to tie it all together because I started with text only, went to multimodal, went to vision only, went to robotics only, and now actually I'm really excited. I think this is kind of our first announcement of a new model that we've actually archive should be out today, and we have a project page out today. We call it Larva, and the motivation is, well, there's a lot of great progress in LRMs. And I'm not sure I've convinced Ilya that language is useful or not, but we can be ecumenical on that. But I think there really is some leverage language models can bring us, and the following work's gonna show you how. And there's like there are not a lot actually, with the exception of the work that Chelsea and her colleagues recently announced this morning. Up until this week, there have been very few public models that are trained on large data sets that have the opportunity to generalize to different settings. There's RT1 that first started this leveraging a language model architecture, but didn't leverage language. RT2 leveraged language, but it was a huge behemoth that's not openly available. Octo is really strong, but it wasn't explicitly built on a language architecture. So what we're releasing on arXiv today is what we call Larva, a llama and lava based vision and action instruction tuning model. And I think there's at least 3 important points to make about it. One is that it's just, I think, one of the first, or coming out this week contemporaneously with the Stanford work, model that trains on a large open data set using an open model, Lava and Llama class models, and showing, as we show, that such an approach actually outperforms a lot of the baselines that were out prior to this week. 2 key ideas in our work, I think, that are specifically noteworthy. One is a structured prompt. And we found that, and I think this is one of the leverages that a language model gives you in robotics, is that having a structured prompt, such as the prompt that we show here, you are a blank type of robot using a blank type of control. These data sets are interleaved with all sorts of different things, different types of robots, different dimensionalities of action spaces. And when you try and make a transformer or any learning algorithm, you pour all this different kinds of, it's like taking SAR data and electro-optical data and putting it into the same thing and having the model have to figure it out without any hints. It helps to give it a little metadata. So we found that one of the leverages that we saw was prompting with a structured prompt, where we told the model what its geometry was, what its control policy was, what its task was, and then have it predict steps. That was useful. So that's the structured prompt. The second thing that we found very useful is what we call a visual trace. And just like in the Sesame and Lisa work, these large multimodal models could predict segments. We said, maybe you should just predict visual trajectories. Like, with forgetting joint control for a second, just like highlight waypoints in the 2D image that you expect the end effector to traverse as it's about to solve this task. And adding that as a sort of privileged side task turned out to be pretty useful. So that's essentially the Lava architecture. Predict future actions given an instruction that describes the robot model, control mode, robot task, and past proprioceptive information. And so different kinds of robots are going to have different kinds of control policies. And of course, there are going to be different kinds of tasks. And so we see that the kinds of the visual traces we believe serve as a mechanism for alignment between the vision and action modalities, and our experimental results support that as well. And these traces are pretty straightforward to generate. You could render them. We actually train a little just tracker that tracks them. So we basically take the OpenX embodiment data set, compute these visual traces on top of it, and add our structured prompt paradigm on top of it, and define that as our new database, and we'll make that available to everyone. And we see that sort of taking these ingredients and essentially applying the standard pre-training and fine-tuning recipe, we basically pre-train on curated subsets of the OpenX embodiment data set, and then we fine-tune for downstream tasks. And as we evaluate both tasks in RL bench and in real-world experiments, we see that both the instruction-based pre-training significantly improves performance, and adding our 2D visual trace as an additional task significantly improves performance. We see generalization across 2 different kinds of simulated robots in this case, and our method. So actually, our method is a 2D perception method, which is a fairly aggressive place to be compared to the recent state of the art. A lot of models use point clouds or 3D sensors, and we could probably use that too. We just haven't gotten to it yet, and I'm not sure it's necessary because we get pretty good performance just with 2D, and our performance really dominates the prior art in just looking at 2D. And it's really competitive and in some cases beats the prior art, in some cases sort of ties it or is slightly behind it if we think about models that are using explicit 3D sensing. Happy to talk about that more offline. And here are some of the results, some of the example videos and results that we have in RL Bench. Here's some of the experiments that we have on a real Franca robot and the performance beating the prior baselines of Octo or the RPT method. And you can look at our archive and for the full set of results, and more will be coming soon. So the key takeaways of this larva project, authors shown on the bottom there, this idea of a structured prompt and the prompt giving the context of task, control, and geometry, the idea of adding a waypoint prediction, intuition, or task to the model is very exciting. And I think these provide alignment. We think this is one of the first sort of vision action instruction tuning methods that we've seen in robotics. So that was the talk today. I think I went on a long path, hopefully ended up on something very relevant to this workshop. But I started basically with the philosophy of we don't know what we know or don't know with regard to text-only large language models. They actually know more about the visual world and the physical world than I would have guessed a few years ago. So we always have to check our assumptions on that front when we talk about language and vision or language and robotics. The class of multimodal models are very exciting right now, even the open source ones that almost any of us can train or certainly fine tune. They take text and image as input, and they can output text and certainly image segments, and as we see, eventually trajectories. We have in our labs at Berkeley really exciting work on vision-only large models and robotic-only large models that are showing real state-of-the-art performance, very exciting. And this last work I'm quite excited about, Larva, which is the first visual action instruction tuning method that I'm aware of. And it shows state-of-the-art performance as well, first open source, or among the first open source large data set trained vision and robotic large language models. Thank you for your attention. I have a few minutes left for questions. Harpreet, I think I've known you since the first conference I ever attended.
I love this idea of combining visual means and language means as a mean for communication. And my question is, when you look at especially hand manipulation data, there's so much more data available for human beings than for robots. So does it make sense to train these models for any arbitrary task to first learn how a human hand would do it, and then have some simple ways of transferring it to hundreds of different types of robot hands? Or is the problem of directly going to robot hands easier, and hence you don't need this?
I think I might defer to some of my. It's too bad Jitendra would have a really strong answer to that one, because he has a whole project on hands. I don't know if Ilya is going to be able to present that work. I feel like there's some part where you're not going to read on the internet a book about the specific joint control of my little finger, right? There's definitely some things we have to learn bottom up just with the embodied controller. But then there are other things that you can, if you want to learn a high level strategy for manipulation, like the fact that I probably like to pick this up like this. All right. I mean, I think I can just show this to everyone in the room. You know this. You can zero shot perform this task. I could probably even have explained it in language, and you could zero shot perform that task. So we want both, because obviously this is useful to have that capability. So I hope that answered your question. Well, and we need more time to what does it mean to see? Like, I still don't want to say it sees. I want to say it can output symbols that are isomorphic with things that I think are seeing like. Now, I don't know if maybe I transgressed in some philosophical discourse there, but So it just means that there are sequences of symbols out there where we see that the word airplane above grass. The models know that airplanes are usually above the grass, or when the airplanes are in the grass, it's a bad day, right? So the language, so does it know that? Again, I'm going to colloquially say it seems like the models know that a crashed airplane's in the grass and a happy flying airplane is above the grass. And that's not far off from what we think about with visual scene graphs. So they know more than I would have expected about visual scene graphs.
That's maybe related to the graph work as well as the larva. So I'm interested in moving from kind of tabletop scenarios where we have isolated objects to, say, trying to extract some item from a densely packed kitchen floor where you have all this junk in it, right? For context, I worked at Amazon Robotics. So these are those within this context of like trying to get this pencil that maybe you just see the tip of and have a notebook on top of it. Do you see any evidence that the language models are providing reasoning for moving from an image of the floor to oh, I need to kind of shove over the notebook in order to get to it and then kind of take this velocity vector out?
I think that's a great state-of-the-art question. I'm happy to talk about that and collaborate in the future. I think I would be most excited about the class of models like Sesame and Larva, because the Sesame models can light the pixels up for the pen easy. And I'm sure that the underlying Llama model knows how to grab a pen and also knows that a pen is smaller than a notebook. And so all the common sense reasoning that we've missed in the pure bottom-up robotics or even the pure bottom-up vision world is coming, crashing down on top of us in a happy sense. And so I'd expect I see no reason to not be optimistic about that in the next year or two. But I can't point to a result today. It seems like that, although I think any super simple answer will end up being much more complicated in the future. And I guess personally, I am a little skeptical that it's the actual causal versus batch issue. I think my intuition is that it's more the regression versus cross entropy loss that might be the more important. I can't believe that you couldn't get similar results with some batch, but I don't know. The empirical results seem to be disagreeing with me on that. But I do feel like there's a difference between regression loss and cross entropy loss, and I guess we'll see as the results come in the future. Oh, thank you all for your time.
of AI and really each of the sub-disciplines. So we've seen this sort of starting with language, with large language models like GPT, PaLM, and so on, and then transitioning slowly into vision and sort of other fields. But I'd argue that the notable exception to this trend really has been robotics. And of course, there's a lot of encouraging work along these lines. I think you've seen some from the speakers earlier today, and you'll see more throughout this program. But we're still relatively early on this journey when it comes to robotics. And for the rest of this talk, I'd like to sort of share some perspective of how we might go about developing large models for robotics. So our journey on this really starts from vision. And so I'll start by presenting this work from Coral 22 on visual pre-training for robotics. So if you sort of zoom out a little bit, and we go back a few years and consider the field of robot learning, things look something like this. So if we have a task that we want the robot to learn, like suppose reaching a red cube, like shown here, what we would do is we would go collect some data, and then we would train a vision model from scratch, and then we would train a motor controller policy on top of this vision model, also from scratch. And that's great. We now have a neural network solution that can reach red cubes. But now suppose we want to pick yellow cubes. Well, we would go and do the same thing again. We would go collect some data, train a vision model from scratch, and train a motor control policy from scratch. A new task, let's say closing a fridge door, again, the same story, and so on and so forth. So for each task, we would train a separate vision model from scratch, and we would train a separate controller. And this seems kind of strange and very inefficient, right? Because as humans and other biological systems sort of use the same the same neural machinery to sort of support all visual tasks. And this is kind of the hypothesis we had in this work, which is really to ask the question of, can we build a single vision encoder that can serve all downstream robotic tasks? So if I were to translate the picture from before into something like this, it looks something like this, where we have many different robot tasks, and we have the same shared vision model that's pre-trained and frozen, and is then used to learn a bunch of different motor control policies on top of the shared visual backbones. So this gives rise to a framework for pre-training visual representations for robotics, which consists of 3 stages that I'll walk through next. So first, it of course all starts with data. So to train our vision model for robotics, we collect we sort of accumulate a large data set of images and frames from the web, and also including everyday interactions like from user-centric videos, YouTube videos that contain things like furniture assembly and so on. But we also add internet scale data sets like images. So altogether, this gives us a data set of about 4 to 5 million images that we can then train on. Now, the challenge with this data is that it is unlabeled, and we don't really know, we don't really have a good objective in mind for robotics. So what we do is we resort to self-supervision via masked autoencoders. So specifically given an image, we randomly mask out the subset of this image, and we task a model to predict the missing context. So we use masked out autoencoders in this context, and it's not necessarily the ultimate objective for this task, but it has a few nice properties that makes it well suited for pre-training for robotics, which is that it does not rely on labels, and it does not rely on data augmentations, which makes it very easy to apply to large quantities of unlabeled and uncurated data. And here, uncurated is quite important because a lot of these everyday images do not have the your sort of typical centered object bias like many of the internet images that we're used to and that we like. And so then, given this objective, we train a vision encoder using for robotics. Now the question is, okay, so why is this a good objective, right? Sure, it doesn't need data augmentations, it doesn't need labels, which is great, but like, why does it make sense? Like, why does reconstruction make sense as a sort of proxy task for robotics? And the intuition is something like this: is if an agent is able to mentally infill a sort of a subset of the environment given the present context, it is likely that it will learn something about the world. So, for example, we have a picture of a plate where a lot of it is occluded. If the model is able to extend the shape and sort of complete the shape, it is likely that it has learned some implicit representations of shape, and similar sort of things for other objects and environment properties. And here I'm showing some of the reconstructions that we get using our model, and this also gives you a bit of a flavor of the type of images that we get. Okay, so given this model, we train this model and we train shader control policies on top. You see the three examples here of sort of reaching, picking objects, closing the door, and so on. So they're fairly simple tasks, but the key thing here really is that all of these different tasks use the same vision backbone that's being pre-trained and frozen. And quantitatively, we see that this approach outperforms a few different baselines. So it outperforms training from scratch, which is the paradigm that's most common in robotics. It also performs supervised pre-training on data sets like ImageNet, as well as, interestingly, outperforms FLIP, which is a model trained on much more data, so 400 million image language pairs. And we thought it was a very interesting result. We suggested for these low-level control tasks, it might be the sort of semantic pre-training like in models like FLIP might sort of be taking away sort of quite important details for fine-grained manipulation. So, and you know, it's possible that it's sort of more semantic tasks that sort of ordering the FLIP, but it's an interesting sort of, I view this as an interesting signal to sort of consider robotics as a downstream evaluation task in computer vision as well. And this model can benefit from more data and larger models, but it's really important that we scale both the model and data together to realize the benefits of this approach. And when we do that correctly, we do get nice scaling properties. And this behavior seems to be more pronounced on harder tasks, which is also quite promising. Okay, so I mentioned that we want general visual representations for any downstream task, but I've only really shown you the same robot doing somewhat similar things. So we wanted to test this idea really by trying these representations of an entirely different robot. So we took this multi-finger hand. We used the same vision encoder, and the only thing we changed is the dimensionality of the actions space. So, going from 7 joints of an arm on a table to sort of 16 joints of the fingers here. And we repeated the same procedure, and we found that the same model enables us to learn tasks with a multi-finger hand as well, albeit fairly simple tasks with the finger cube, but still a nice signal for general visibility of this approach. Okay, cool. So we've seen that visual pre-training helps in a few different regimes, but the question is, can we retrain more than just visual representations? Because the robotic is sort of a richer problem than vision only, and then can we do more? And this is the sort of the question we explore in our oral 2023 paper with Weifang and other collaborators over here. But before we dive into it, let us take a step back and consider the robotics problem. So it looks something like this. So we have a robot that's operating in an environment. This robot is equipped with certain sensors that let it sense the configuration of its own body. So joint encoders typically that sort of tell us essentially how the arms are positioned, as well as some number of sensors, like typically cameras. So here you can see 3 different cameras that are sensing the environment. So together, these measurements, these proprioceptive measurements that describe the body of the robot, together with different cameras, get fed into a controller, and then this controller output desired actions, which are typically sort of the configurations of the body to reach in the next step. And then these actions get fed back into the environment, which then gives us new readings and so on. So if you think about this process, you can really think of it as sort of being a data generation machine, where we have this loop that's constantly generating data. And this data has a few interesting properties. This data is sequential and it's multimodal. So at each time step, we get access from sensory observations from multiple modalities, sort of robot proprioception, vision. You could add things like touch, sound, and so on. And then we have this over time. So we refer to those as sensory motor trajectories, which is sequences of these multimodal observations. Cameras, proprioception, and action, and then all of this over time. And we really think of this as being the language of the physical world, where this is really the sentence that this is how we express the physical reality. And then when you take this perspective, this suggests sort of a simple pre-training approach for robotics, which looks something like this. So given a robot trajectory, that's a robot picking up and stacking the cube, we get this sequence of multimodal observations. We can then randomly mask out a subset of the sequence and train a model to predict the missing content from the visible parts. Very much the intuition like before, and very much like the BERT objective in natural language. So let's look at this again. So given a sequence, we get camera images, we get proprioceptive streams, we obtain a sequence of multimodal observations, we mark out the subset, and we train a model to predict the missing parts from the rest. So at the core of this approach is sensory motor prediction, right? And you might again ask, well, why does this make sense for robotics? If I want my robot to to do laundry or to stack cups or empty my dishwasher, why should it be able to do this silly prediction task? And the intuition is sort of, I guess, something like this, which is that by learning to predict the missing content, the model is implicitly acquiring a model of the physical world that should then make it easier to learn new tasks downstream. And indeed, there's actually a lot of evidence in human learning motor control that the prediction is central to motor control and is central to intelligence at large, if you want to get more philosophical. But it's sort of really the simple objective of prediction gives rise to something that's quite a bit more, that's sort of more too much understanding. Okay, so given this model, we can then fine-tune this model on task-specific data. So suppose we pre-train a bunch of different data, then we want to learn a specific task. Then we can treat this as sort of a supervised fine-tuning problem where we let the model observe the full context, the full history of observations and actions, and we just apply the mask token at the last time step we predict from which we predict action. And this is what we supervise the model to do. So this is very much like sort of supervised fine-tuning for the classification data, so it's just being done on actions. And then we can roll out this model aggressively, sort of providing the mask token in the time step, predicting an action, feeding that back in together with observations and repeating this process. Okay, so we've had this framework for sensory motor pre-training now, where in step one, we pre-train a model on a ton of sensory motor data, and then in step two, we behavior fine-tune it on a specific task that we care about. And I've spoken about both of these steps so far, but I really haven't said anything about where do we get the data. And to get the data for this, we collect a data set. We collect a very large data set of 20,000 real-world trajectories over the course of 9 months. This data includes a bunch of different tasks, including simple motor control tasks like picking, stacking, de-stacking, as well as sort of slightly more complicated bin picking tasks with more objects, more pattern. This data is available if you would like to try it. And if you find any, have any questions about it or find any issues, please feel free to reach out. But okay, after pre-training of the data, we can fine-tune our model on downstream tasks. So here we consider simple evaluation tasks like picking, stacking, and de-stacking. And quantitatively, we see that pre-training brings considerable improvements in sample complexity. That is, we need fewer demonstrations to reach a certain level of performance when the model is pre-trained compared to when the model is not pre-trained. So specifically here, we're comparing two variants, one that is trained from scratch and one that is pre-trained. And we see that pre-training consistently brings improvements. And notice here, training first. In both cases, the vision model is pre-trained. So when we say scratch, we really mean pre-trained vision model, but the motor control model being trained from scratch. If the entire model was trained from scratch, the performance would be quite a lot. Okay, and then this approach scales with model and data size. We see benefits from using a larger model, larger context lengths, and larger data sets. But perhaps the most interesting result to me here was the fact that we attain positive transfer across robots in different labs. So if we pre-train our model on one robot in one lab, we can then use that the checkpoint essentially to perform transfer to a new robot in the new lab. Sort of, it's the same type of the robot, but it's in a different lab. It has different cameras, different configuration, different table, different environment, and so on. And the gains are substantial compared to training from scratch in a new environment. But it turns out that we can actually do the same thing across different robots. So here we take data from one robot, sort of the X-arm robot, and transfer that to a Franken robot. So in this case, the settings are quite different. In the case of the X-arm, the control frequency is 5 Hertz. It has only one camera. It's a different environment, collected on sort of no velocity measurements and so on. And then Frank is quite different. And there's still transfer. So I'd highlight two results here. So first, we see that pre-training, even on a different robot, brings substantial improvements in performance. And two, it comes pretty close to pre-training on the same type of robot. So, if you kind of think of this as sort of pre-training from, the robot A to robot A, that's kind of your upper bound for pre-training from robot B to robot A. And we come pretty close to that. So overall, I'd say these results are a pretty promising signal for training general purpose robots, robot models on diverse data sets that also include different robots. And one interesting thing we also noticed is this sort of emergent self-correction behavior where the model will sort of, if the model fails to grasp a lemon, for example, it'll back out and retry the behavior again. And what's interesting here is that this data was not seen during training. So this model has was not trained on any trajectories that contain failures, any trajectories that contain sort of retries or anything like that. It was purely trained on trajectories of successful behaviors. And we only see this emergent behavior if we train with this prediction objective. We don't see this if we perform supervised learning on data, which was an interesting sort of property. Okay, so far we have talked about pre-training for vision and pre-training for sensory motor data, but we've only really done this in fairly simple tabletop environments. And the question is, can we transfer some of these general purpose algorithms to general purpose embodiments? And in particular, one that I'm really excited about is the humanoid embodiment. And it's also a good time to be talking about that, as there's been a lot of excitement in the field and in the community about humanoids. So this is Jensen Huang earlier this year at GTC giving a keynote where he featured humanoids quite prominently. Which is good. And then indeed, we really like humanoids, and we started working on humanoids a few years ago. And we started with the basic skill of walking. So here is our robot walking over the Berkeley campus. So this is the digit robot from Agility Robotics out of Oregon. And we purchased the robot off the shelf, but then we write our own software, so everything is being controlled by our neural networks end-to-end. So sensory observations from the robot coming, and then our model controls the robot. So this is a very large robot. This robot is about 160, 170 tall. It has roughly 50 kilos, so it's a full-size robot. We control it at 50 Hertz, everything, all of the computers on board. And one thing that's interesting is that everything you're seeing here is blind. So this robot uses no vision. Our controller uses no vision. It's acting purely from the proprioceptive observations. And the way we do this is through a general transformer architecture. So we have a transformer that's trained on the history of observations and actions, so very much like before. And then it predicts the next action. And that's it really. So sort of raw sensory observations from a high-dimensional humanoid go in, and out comes the next action, and we repeat. So there's no domain-specific knowledge that's being designed into the architecture, not domain-specific action spaces or anything really. It's all being done purely end-to-end and then deployed on the humanoid robot. Now, the way we train this is in simulation. So it's very difficult to obtain data on the humanoid until you have something sort of working a little bit with having problem. So we have to start from scratch. And the humanoid is sort of a hard platform to do from scratch in the real world. So we do this is simulation. So in particular, we simulate thousands and thousands of different variations of our robot by sort of slightly changing different parameters of the physical world. So sort of changing friction coefficients, changing masses, changing sizes, changing scales, randomly pushing these robots and so on. So we can think of each of these robots as living in its own little virtualized world. And each of these worlds is slightly different. So the intuition is that if we can train a single neural network to control the robot across all of these different virtual worlds, then we can think of the real world as just being yet another instantiation of this, of the universe. And then that's sort of point number one. And then point number two is that through walking in every one of these different worlds, the model can, from the past history of observations and actions, sort of sense and figure out which environment it is in, and then adjust accordingly. You'll see some experimental evidence of that next. But okay, after training on the simulated world, we deploy our robot into the real world, zero shot. So we have no additional fine tuning, no training in the real world. It's been trained entirely in simulation and then transferred to the real world, zero shot. So a robot takes as input the desired heading commands, so the velocity forward, velocity sideways, and the linear velocity forward and sideways, and then the angular velocity for turning. So these three numbers specify the directions and speed in which we want the robot to move. And it can follow arbitrary combinations of these three values to achieve omnidirectional walking. So at training time, we randomly sample different combinations, and then at test time, we provided via joystick. One interesting thing we noticed is that this robot features this arm swing behavior, where you see sort of the left arm goes forward together with the right leg, and then the left leg goes forward with the right arm. And this is, and then that got us thinking, and it's really actually a peculiar feature of human walking. It's not entirely obvious. Okay, so why do humans swing their arms while they walk? Why don't we just keep our arms sideways, or sort of swing them in cycle with the legs? And this was kind of something that we found interesting, and then we went on and read about it a lot, and it turns out this is a very well-studied phenomena in biomechanics, and there are various different hypotheses for why this might be. I won't sort of go into that too much detail, but the short story is that it seems that swinging your arms dynamically is the most energy efficient way of walking. So when researchers compare different ways of swinging or keeping their arms on hold, it turns out to be the case that humans consume the least energy when they swing their arms. And this is also interesting because one of the sort of reward terms as part of our reinforcement learning objective function is to minimize energy. So we don't know for sure that there's a causal relationship here, but it's an interesting thing to consider. Next, one interesting phenomena of our model is that it exhibits in-context adaptation. And what I mean by that is the ability of the model to change its actions depending on the context or terrain it is in. So let's consider the following experiment. We're going to have this robot walk over flat ground, then walk down slope, then walk over the flat ground. And let's see what happens. So the robot starts by lifting its legs. Then it goes down and it's sort of making these small steps, not lifting legs very much. And then when it's back on flat, it sort of starts lifting its legs up again. And so this sort of change in behavior is entirely emergent. This is not something we pre-program. This is not something we train for or pre-specify. We sort of see this emerging context. And this suggests that the model is somehow able to figure out its environment, even though it's blind and even though it wasn't trained to do so. And then we looked into this a little bit more. We looked into it quantitatively. And we performed analysis of the learned representations of this type. And we see three things. So first, we see that there are certain neurons, or certain units in the transformer latent space that correspond to gait frequency. That's when the robot is lifting its legs, they sort of they're high, and when the robot is making small steps, they're also small. Second, we see that there are some other neurons that seem to correlate with terrain, which is their responses are high on flat ground and their responses are low on slope. And even if we take all of the activations in aggregate, and we just sort of take the full latent representations and we project this to 2D via PCA or TSD, we see that the representations cluster quite nicely depending on the terrain the robot is walking. And so this suggests that even though this model was never trained to classify or reconstruct or in any way sort of represent terrains. As a side effect of learning how to walk, it has acquired world representations that capture some of these properties. Next, there's sort of a similar experiment, which is because our robot is blind, it can't really anticipate obstacles. So if we sort of just have it walk forward and there's a step or there's some sort of a discrete obstacle, it will hit it, right? And then when it hits it, what we find is that the model figures out how to recover from that very quickly. So let's see how that works here. The robot is walking, then it hits the obstacle, and then on subsequent attempts, it lifts its leg higher. So the intuition here is that even though the model cannot see the environment through an external facing sensor like vision, because it has the history of desired and achieved actions, it can figure out how to sort of change its actions to achieve the desired state. So for example, if it attempts to cross a step a few times and it sees that it's not achieving what it wants to, then on subsequent attempts, it can exert more torque to lift its legs higher and faster in order to attempt to do this. And that's exactly what we see happening here. And the model was, by the way, never trained so that the simulated environment would not get any forms of discrete obstacles or any forms of steps. Okay, and then we see this sort of quantitatively again. If we look at the neural activations of this model, we see that these events that correlate with hitting the steps and so on are very clearly represented in the distribution of the representations. Finally, this model is very robust to external disturbances. We can throw yoga balls at it, we can push it, we can pull it. It's pretty hard to make it fall. And this is in part because in simulation it receives a big punishment for falling, so it really tries really hard not to fall. Okay, so a few takeaways. So this was a first fully learning-based approach for humanoid locomotion, trained entirely end-to-end with reinforcement learning with massively parallel training and simulation. And it's also the first approach to use the transformer architecture to perform humanoid control end-to-end. And this has a few nice properties like in-context adaptation that emerge as a side effect of training, and they enable us to zero-shot transfer this model to the real world. Okay, so we've had a model that's fairly general. So it's a transformer architecture. It was trained with large-scale reinforcement learning. And then we're sort of curious, okay, how far could we push sort of a sequence modeling approach for real-world humanoid control? So it seems like, because it seems like the task is very dynamic, it's very sensitive to errors. Like, could we train a model by pure sequence modeling that can still control this large robot system in a highly dynamic way? And this is the question we studied in our recent work on humanoid locomotion as next token prediction. So to do this, we devised a framework that consists of 3 stages. So first, we need to collect the data sets of humanoid or human walking, which I'll talk about next. Then given this data set, we train a transformer model by a next token prediction to model this data. And then we deploy this model, in our case, with various locations in San Francisco. And so let's look at each of these in slightly different. So our data set consists of trajectories from 4 different sources. So first, we take trajectories from our previous controller that we trained in the previous paper. And then these are really nice because these come from a model that controls the exact same robot morphology, and we get full access to whatever measurements we like. We can get access to observations, joint positions, we can get access, but most critically, we can get access to the exact actions that the policy took. Next, we get trajectories that come from a model-based controller. So here, this is essentially the controller that ships with the robot. So we can record observations from this controller, but we don't know how it works. We can't get actions or any sort of underlying information. So we only get sequences of observations, but it's still kind of nice because the robot morphology is exactly the same. Then we take some amount of lookup data. So here, this data is recorded by humans in the lab. So the data is quite clean, it's high quality. But the challenges are two. One is it comes from a different morphology, human versus a robot, and it also does not contain actions. And finally, we take data that comes from internet videos. So specifically, we run pose estimation methods from computer vision on large-scale video data, and then we essentially treat this as a noisy version of mockup. So this still has all of the challenges, the same challenges as mockup data, and in addition, it is noisy. So you can kind of tell that different subsets of our data have different trade-offs in terms of scalability and quality. So here's how some of the sequences from YouTube look like, from which we gather data from human videos. And one thing that's kind of nice here is that even if a sequence has many people, we can get multiple trajectories from the same sequence. And then given these sequences, like for example, walking or running, we can reconstruct this sequence to estimate the pose of the human in those scenarios. And then given this pose of the human, we can retarget this onto a robot simulation. Now note that here the retargeting is super noisy, it's sort of kinematic, it's not dynamically feasible. But that's okay with our approach, because we even if the data is, some of the data is noisy, in aggregate it's still come. But now the main conceptual challenge in this setting is the fact that a lot of our data does not come with actions. So we do not know what are the torques, whether the desired actions that the robots or humans do. And we solve this by performing sort of a simple but important change in how next token prediction is being done in the multimodal setting, which is that at each time step, we predict the next token of the same modality. So rather than predicting the very next token, which might come from a different modality, we predict the next token from the same modality. So in this case, for each observation, we predict the next observation. For each action, we predict the next action. And what this does is this essentially turns our training approach into an unpaired one. And we can now readily benefit from unpaired sources of data. So if we have trajectories that only contain observations, that's fine. We can still predict whatever we have. If we have trajectories that have both observations and actions, even better, we can predict both observations and actions. But this sort of change enables us to train with data that has any subset of modalities without any issues. And finally, so once we train this model, we deploy it to different locations in San Francisco. So we have it walk over a bunch of different places. And so I think that's worth highlighting is that deploying a robot in a city environment is a lot more challenging than deploying it in the lab or even sort of in on university campuses, because it really has to work. These environments are very dynamic. There's a lot of people. The policies sort of just need to work, which we found is like a really nice test bed for real world deployment. Okay, so quantitatively, one thing that we find is that these next token prediction policies tend to produce smoother and nicer gates than our previous RL policies. Here you can see sort of a plot that shows one of the critical knee joints and how it behaves. And you see that the policies trained with next token prediction are a lot more smoother, which also is visible qualitatively. One thing that I found really nice is that the prediction error of this sort of modeling the joint distribution of observations and actions correlates strongly with walking performance on the task metrics, which is a great signal for scaling these next token prediction type approaches. And indeed, it benefits from more data from larger context lengths and larger model sizes. Another thing that's quite interesting is to see that we saw generalization to unseen commands. So we designed an experiment where we trained our model on data of walking forward only. So it only ever saw trajectories with the head of the robot walking forward. Then at test time, we prompted it with a command to walk backward, and the model can achieve the hero shot completely without seeing user training, which we thought was very interesting. Okay, so main takeaway. So this really is that we passed real-world humanoid control as a pure next token prediction problem. And we propose a general framework for training with basic data. Then these together enable us to train a model that can then work humanoid in various locations in San Francisco. So sort of zooming out, in this talk, we've seen four papers. So first, we started with visual pre-training from internet videos for robotics, or pre-training vision encoders and then using them to various downstream tasks. Then we moved on to sensory motor pre-training, where we pre-train our general transformers models on both vision and proprioception. Then we looked at the fully end-to-end learning based approach of humanoid and locomotion with transformers and reinforcement learning. And finally, we've seen how we can cast humanoid control as a pure next token prediction. With that, thank you very much for listening, and I'd love to take any questions.
Questions?
Thank you. It's really, very interesting results you got. I was just wondering, I am both a physics simulation person and robotics person, and for the last 7 or 8 years, machine learning person. And I've been kind of thinking, and I'd love to hear your perspective. The very fact that we have these large data sets of trajectory data, and what really all these neural networks doing is doing signal reconstruction from these data sets. And so implicitly, the neural network is actually constructing the signal of the curves of these control law. And whenever you do any kind of perturbation, it's sort of kind of perturbing a little bit, sampling. So when you do fine tuning, it's like taking a time stepping. And so we actually expect to see the kind of result we see. My question is, do we really need to do what we're doing for these large data set learning? Are there some sort of unified representation that we should be really thinking about? Because what we are doing, next token prediction, is just simply time stepping. Do you see what I'm saying?
Yeah, so let me try to comment on that. So I think the objective of next token prediction is very simple, but it's quite profound in the sense that, I'd argue that predicting what comes next requires understanding. And I'd say that I'm not sure if I share the intuition of sort of, reconstructing statistically patterns from our data set, because, such models would sort of simply output the most likely thing that was seen in training. But I think with the modern neural networks trained on next token prediction, I think we see strong evidence of models sort of doing more than just that. Because these are general purpose computers effectively trained by creative consent. And it's I would say conceivable that by forcing these models to predict what comes next, we're really forcing them to understand. And I think it's quite a powerful objective.
Okay, I think we need to have a separate discussion because I'm not sure where the understanding is. What I do see is a signal reconstruction of the mathematical equation that describe the phenomena that we have, right? And if we have any instance in time in that curve, the next token prediction is when you take that particular location, you predict what will be next. It's time stepping on the curve. If the signal processing works.
Yeah, well, I don't, we should take offline. A quick comment is that, I think it'd be difficult to come up with equations that sort of, represents the richness of the physical world, to feel like, and but maybe we can take it offline.
Yeah, I'm just curious, your robot was blind and it was, I assume, part of the loss function was that it shouldn't fall. And that's why it was careful. he didn't use his arm, its arms though. So I guess that's just because when you did that simulation that there was no way it could be hitting something on top. Otherwise, I'm just curious, but maybe he did some work like because a blind person would kind of use it.
Yeah, no, it's a good point. So we did not train with any obstacles. And it's interesting to see what happens if we did have some work with it, develop more cautious behavior, right? Yeah, we haven't done that. Yeah. It's sort of purely blind and pure walking. The intention was something like alluding to, right? We know that blind humans can walk, and walking is sort of seems like a simple first step towards layering more and more capabilities on top as we go on.
And have you done any work towards it not destroying something? In other words, being careful in not hitting and destroying something. Have you done any work in that?
No, but I do think that's a major and an important area for research, especially when it comes to deploying these things in everyday environments. With humans, pets, as well as the material properties.
I'm curious about when you learn to predict, aren't you biased towards the common cases and then like walking straight, but then when there are anomalies, how do you still know how to predict them?
Yeah, so harder and less likely examples are definitely harder to deal with, but I think we've seen quite substantial evidence that the model is still able to deal with things it has never seen, like these steps, or walking with sort of different habits. So it seems to be the case that it's learning something. To my previous point, so a little bit more than just repeating the most likely pattern in training, because these are not simple training.
Do you do something special for them, or just
really not so? Yeah, it emerges as a side effect of training, and I think that really, so this is where my intuition comes from, is that neural networks are lazy. They'll do the easiest thing to achieve the task, right? And it turns out to be the case that if you set up your learning problem right, so you have a powerful transformer model, general purpose computer, have a lot of data, then sort of the easiest thing to do is to do the right thing, and to really understand the task, because that's the easiest way to actually predict. It's much easier than to build statistical tables and so on. So that's why I think in part these models develop a rich understanding through prediction.
I think we can answer the last question.
Yeah, you described a lot of data sources. Have you done evaluation experiments about how much those are influencing it? Like, could you learn without mocap data, for example, or without actually any of the simulation data? And also, I'm curious for the simulator, how important is the actual physical accuracy of that?
Right. Yeah. So I'd say that we've done some analysis on that, and having some amount of data with actions is absolutely critical. You could learn to work without any action data. In addition, adding the data without actions helps, but the model could work even without it. And when it comes to the simulation accuracy, our simulator is pretty imperfect. It's very, there's a various reasons very hard to simulate a specific robot. So it turns out that we can achieve transfer even with sort of a fairly inaccurate simulator, but we do have to randomize a lot. So it's one of those things where you want to be either super accurate or have many different randomizations. You don't want to be in a spot where you have a few inaccurate ones. So we sort of get around this issue by randomizing quite well.
I think we are on time, and let's thank our speaker again for this wonderful talk. We will resume the afternoon session at 2 p.m. and for those who want to see the posters, it will be the ARC building, 4th floor. Thank you, everyone.
我们要开 video。开 video。
开 video 随便是 video 随便。
video 其实看也看不到，我觉得不看了。
可以的。你要这个画出来吗？
这个可以吗？呀，我觉得随时都可以开始。
Okay, let's get started for our panel section. So our next speaker is Dr. Fei Xiang. And Fei is a senior research scientist at Google DeepMind, where he worked on the robotics team. He received his PhD degree from the Department of Electronic Engineering at Stanford University. He was co-advised by Professor Silvio Tavares and Professor Leo Huilas. He was supported by Stanford Graduate Fellowship and Qualcomm Innovation Fellowship during his PhD. And he has done research internships with Dieter Fox at NVIDIA, Alessandra Toshiv, and Brian Eacherter at Google. He obtained his bachelor degrees from Tsinghua University in 2016. Let's welcome our next speaker, Dr. Fei Xiang.
Hi, everyone. Thanks for coming, and I'm super happy to be here. Today, I want to share some recent progress on using vision language models in the domain of robotics. I will be talking about towards generalizable motion level intelligence with foundation models. I'm from GDM robotics team and happy to share the progress. Most recently, I have been working on using foundation models for motion level intelligence. Let me briefly explain how we arrived at this point. So recent years, we have seen rapid progress in using foundation models in the domain of robot planning and autonomous vehicles, right? But mostly these applications have stayed on a reasonably high level, like people have been using vision language models or language models to do high-level planning and reasoning. However, it is not super clear how we can make those models to generate precise low-level motions. That's what I want to tackle in my research. We have been using foundation models to do lower and lower level control in the recent years, and we have seen some signs of life of motion level intelligence. Let me give you some examples of what I would call motion level intelligence or generalization. Those are not completely working yet, but we see some signs of life. First, the piece of results is coming from RT2, Robotics Transformer 2. This is the second iteration of the robotic transformer work that our team have been working on. We are basically using imitation learning to train a large vision language model in this case, and there are some signs of life for motion level generalization. So first of all, we ask the model to basically arrange the object in a novel way. We ask it to, for example, put the banana near the number 3 or put the banana near the German flag. However, in the training data, there are exactly 0 examples of such demonstrations. The demonstration only involves about 17 objects. It has never seen these objects, like these novel objects. We have to buy them from the dollar store. But the robot is able to do that. That is because we start from a vision language model that has been pre-trained on the internet scale vision language data. So it has already the semantic prior in them. So it can do some motion level generalization. It can also do some sort of reasoning. In the bottom row, I showed a couple examples. For example, pick up the green object or move the green objects together and understand which are the green objects and can generate a motion to do that. We can also do chain of thought reasoning with a vision language model. So chain of thought reasoning is a commonly used technique in large language models to elicit reasoning behavior and solve complex problems. It is not super clear how it can be applied to the field of robotics. However, we find that instead of generating the action tokens directly, instead of letting the model directly generate action, we first generate some sort of rationale and then generate action. The model can generalize better. So the first part is like a visual question answering problem, and the second part is like a visual motor control problem. So it basically string the 2 tasks together that elicit generalization. There are some other signs of life for general motion level intelligence. is that we can use language model. We can ask language model to generate pieces of reward code. And then we can use the reward code as a goal and use some off-the-shelf optimization methods. Here, we are using MJPC, which is Mujoko MPC. It's a optimization, black box optimization framework that can take in the reward and constraint and then solve the motion for it, right? So we combine the semantic understanding of language model. So for example, here, we teach the model, teach the robot to do a moonwalk. A moonwalk is a very complex motion. It is require the robot to move backward, but swing the leg as if it is moving forward. So the language model can decipher this type of motion and generate pieces of reward code where a low-level policy, in this case, a black box optimizer can solve for it. So this is another kind of science of life for motion level intelligence. It is coming from the semantic understanding of large language model and the low-level optimization from optimizer. There are some surprising, what I call failure case, but it also shows that you can generate a novel motion, which is the name of the game here. We can generate, so here I asked the robot to pick up the apple, but it picked up the apple in a surprising way that I don't really want. But nevertheless, it is still showing that you can make the model to, yeah, it's almost like a stunt, right? It's picking up the apple in novel ways. So while in like using traditional imitation learning, or if you just train large model, it probably cannot do that. So there need to be some sort of structure. So that's a brief introduction of what I think we should work on is motion level intelligence. We have seen some exciting demos from different robotics companies. So on the left, we show a demo of the Figure.ai, which is a humanoid robot company. It can do a fully learned, fast and dexterous manipulation. It is we don't know what exactly is the technique behind it, but from similar lines of work from other companies, we hypothesized it might be imitation learning. How generalizable is it is another question, and is what we want to address in this talk. We can see another video from another company called Astribot. It's super impressive that it can do dexterous motion. It can generate a smooth and dexterous motion and deal with a very complex environment. But every time I see this type of video, I would poke around it. I will ask a couple questions. So first, does it work for other objects? Or does it only work for the constrained set of objects that the robot is presented with? Second, does it work for a cluttered environment? Real world is really complicated. So if you go to a cluttered kitchen scene, can the robot still do it? And can the robot interact with human naturally, right? The most unstructured element in the environment is probably human users. And third, can the robot compose the motions in different ways, right? So if it is just a pick and place, I wouldn't call it general motion level intelligence. Can it use articulated objects? Can it use tools? Can it operate constraint mechanisms such as opening a door or cabinet or drawer? When we talk about door handle, we see different shapes of door handle. Can it work for different shapes of door handle, right? So that bears the question, how can we achieve the motion level intelligence? Or to solve that question, let's first have a loose definition of what is generalizable motion level intelligence. So first, you need to adapt to new objects and new environments. It's a must requirement if you want to deploy those robots in human homes. Second, you want to generate new motions generalized to new verbs. And third, instead of just generating the action, the agent also need to understand why exactly it generated that action, because that level of understanding is quite important for generalization. And finally, the model ideally should also have some world understanding, some world modeling. It need to understand the effect of actions. This will make the model plan effectively to avoid dangerous actions, for example, and generate optimal actions. Our team, GDM Robotics team, came a long way of using foundation models to do lower level control. It's a quite novel concept because large language models are previously trained mostly on text domain, right? So generating motion is not their strong suit. So planning is much more intuitive because there are a lot of planning related text corpora on the internet. So at the beginning, we're mostly using foundation models for task level planning. We showed in the work SEICAN, where you can combine a large language model with affordance functions to do long horizon planning, and the model can respond to human queries and solve a long horizon task. And for the low-level policy there, we mostly use a smaller model. It's not a foundation model. In that case, we use RT1. But more and more over the years, we find like to fully get generalization, to fully leverage the internet scale data, and to jointly scale vision language training and robotics training, we need to leverage foundation models for lower level control as well. And as you can see, the green block represents where we're using foundation model, and the top represents planning, which is more higher level. If you go down, is more like lower level motor control level. We're using the green block to do more and more, which means like increasingly we're using foundation model to do not only planning but also low level control, and we find there are interesting ways to enable that. Like in this talk, I will focus on a couple works, including Pivot and LMPC, which are some of the most latest work this year of our team using foundation model for low-level control. And I also want to shout out to the other vision language model team within Google. For example, Poly is being presented at this CVPR. We are using Poly to do some of the as a backbone for a lot of our robot control tasks. And just because robotics task is quite similar to a vision language modeling problem, that we can reuse vision language model as a very general interface to absorb a lot of our tasks and to basically treat motor control, visual serving also as a vision language modeling problem. I want to introduce a few frontiers of vision language model and robotics, right? So we have established that we can use vision language model to go lower and lower from planning level to do low-level manipulation. There are a couple recipes that we think can fully leverage vision language model for robot control. First is we want to mine existing signals from vision language models. So vision language models are trained on basically the entire internet of vision language data, and some of maybe some part of the data is very suitable for you to develop robot control. So we want to mine and amplify that signal. I want to introduce a work on that. However, if the signal is not strong enough, we want to improve what if you find out vision language model are just not good enough for your task. There are two ways. First, you can improve the core capability of a vision language model. We did a case study of improving the spatial reasoning, spatial understanding capability of vision language models through supervised fine-tuning, which I will introduce a second. And finally, I want to introduce another work which let a user to interact with a language model or a vision language model, and through interaction, the vision language model gets better, or the language model improves with human feedback. It's like a RLHF, but in the robotics domain. The first work that I'm going to talk about is Pivot, iterative visual prompting elicit actionable knowledge of vision language models. So as I mentioned, the vision language model has been trained on a lot of internet data, and some of the data in its training set is particularly interesting. There are parts of the data that involves human annotating on images, right? Like human drawing on circles. And in vision language model, there are parts of the data that are just like that. Because there are such data exist in vision language model training, people have found out you can do visual prompting with VLMs, just like how you do text prompting with a large language model. So you can essentially guide the attention of a vision language model through drawing circles, or you can present a few options and give it to vision language model to score. So our work is built on the intuition that you can leverage this manifold of training data where there are drawn annotations on the image. There are also annotations on the image that correspond to intention or actionable, right, knowledge. For example, on assembly manuals, right? You will see arrows, and those arrows have semantic meanings. So we want to fully leverage that and see if we can elicit actionable knowledge from a pre-trained vision language model. So this work, we haven't fine-tuned any parameter in the vision language model. We just see zero shot, can we use it for control? And we found we can do it reasonably well. So for example, we use visual prompting to guide a robot to do a navigation task to find a wooden bench. We present the options as markers on the image, and we ask the vision language model, which of the arrow is the best to guide the robot to a wooden bench, right? And we use a procedure called iterative visual prompting, which I will introduce next. And we find it can guide the robot to do a few semantic tasks reasonably well. Like, for example, it can even do obstacle avoidance through just visual prompting. In another example, we use visual prompting to guide the robot to put the orange in the bowl or put fruits in the bowl. We haven't specified which bowl it should put in. It's just fully like guided by vision language model, guided by the semantic prior of vision language model. And as you can see, it will basically put the orange in the orange bowl and put the grape in the grape bowl. So it's like playing the game of like clustering things that are close together to each other. So yeah. The pivot method, because, well, there are some data in the training set of vision language model, but such signal is quite weak, right? It's quite noisy. So how do we mine the signal from the vision language model? How do we amplify the signal? So we need to do iterative prompting. The procedure works like this. So first, we randomly sample a bunch of actions, and we overlay the action as markers on the image. Right, so at the beginning, it starts with a Gaussian distribution. So it's just as at the beginning, it starts with a Gaussian distribution of the direction and magnitude of the action. Second, we ask vision language model, which one is the best, right? We ask the model, give me the top 3 options that can guide me to finish a task. And then we fit a distribution of the selected action, and then we sample a little bit more. So we repeat this process until it converges, and then we execute the action and then do it over and over again. This process is kind of like particle filtering. Like when you have a super weak signal, you basically run the sampling over and over again. We can also run, for each step, we can also run multiple times and run some sort of ensemble. So this way, you can do temperature sampling and then like basically let the noise of each sampling cancel with each other and amplify the signal. Because this is a super universal interface, right? It's basically just marking on the image and then execute the action that the vision language model chooses. It's a very universal interface. So it enables native cross embodiment, right? You can use it for a robot that does manipulation. You can use it to apply it to a robot that does navigation. You can also do object reference resolution. Yeah, it can represent different type of tasks quite well. We made a few, we find out a few design decisions in our pivot work is quite important to get good performance. So first, we find out our iterative optimization is actually important because, as I mentioned, the signal coming from vision language model is quite weak. So if it cannot choose the right action at the same time, at the first time, you would want to run the sampling process over and over again. And as you can see, usually the error decreases. And if we are looking at the comparison with the ground truth action, we measure the L2 error. It also decreases with a number of iterations. Right. The other thing that we found is that ensembling helps because the process is noisy. So you need to sample multiple sets of actions each time to achieve good performance. I'm mostly excited about the scaling performance. So if I am honest, like this method works zero shot, but the performance is quite low. I will lay out a few limitations in the end, but I'm excited about the scaling performance. So we run this vision language based zero shot policy on different sizes of Gemini models because we have access to that. And we find with the number of parameters increase, the action generation performance also increases. This is particularly exciting because even current generation of vision language model is not capable enough to guide an agent to perform a task at 0 shot. We have a glimpse of the future because when we scale up the performance, when we scale up the base model, we can assume like the performance go up. So basically on the left is open loop performance. By open loop performance, I mean what is the token error, for example? What is the direction that the VLM chooses versus what is a good direction? So open loop performance is a good indicator of closed loop performance. Closed loop performance is a more end-to-end metric. It means how often are you successful on the task? So we can use this open loop performance as an indicator for the closed loop performance, right? And if we establish this correlation, then we can think of basically open loop performance is like perplexity, and closed loop performance is like a decoding accuracy for the VQA task. And we can extrapolate on this on this line. And one day we hope Gemini X or GPT-X will have performance Y on 0-shot robotic control. Like if we can establish this scaling law, then we kind of know through visual prompting, we can get good control performance, right? So this is super exciting to me. Because this is a quite a general framework, it works beyond just manipulation and navigation. Here is an exciting example. This is by prompting GPT-4V. We asked the model, where should I put the orange to make a smiley face? And as you can see, it is always, the arrows are always sticky to the place where there should be an eye. So this is actually quite different from your common object detection or localization task. It is called localizing a concept, right? It's localizing where you should put the orange to make a smiley face. It requires a lot of reasoning. And we find GPT-4V just works out of the box for this case. So this is quite exciting to me. There are some other tasks. For example, I'm thirsty. What should I get? And it can guide a human hand to grab the bottle, right? So it's like you're playing your daily life as an RPG game, and you can use visual prompting to help you make decisions. And finally, where should I throw this away? This is a recyclable can, and as you can see, vision language model can also read the text. And well, in this case, I'm not even sure if it's reading the text, but it can guide you to put a can in the recyclables. There are a few, let's see, there are a few limitations, right? The vision language model is very good at semantic reasoning. We want it to do more fine-grained control, but at this point of time, they still have limited ability to do fine-grained control. So here we plot the distribution of errors over the course of an episode. The higher the better. The higher means your action is aligned with your ground truth action. And as we can see, it first goes down and then goes up and then goes down. So my interpretation for this trend is because at the beginning of an episode is what we call a robot execution trajectory. At the beginning of the episode, the action is unambiguous. You just need to grab the thing, right? It's very easy to predict. When you are approaching the thing, then it becomes a little bit harder. Like you need to close the gripper, you need to like position your gripper fingers in a particular way, and you see a low accuracy here. You see a high error here. And when you grasp it, like usually you have some sort of purpose, you will reposition it, and that part is easy. And finally, when do you choose to finish an episode is also hard. So vision language models still have limited ability to do fine-grained control. And not only that, I just mentioned closed loop performance. Currently, Pivot has horrible closed loop performance. For example, it can do the task usually 30% or 60% of the time. It's not practical, but it's shows some signs of life where you can do more generalization. The lesson learned here is that you want to put, as a roboticist, we can do an engineered solution and we can make it work really well. But we also need to resist our temptation to do that, because the more robotics inductive bias we add into the system, the less it can generalize. Your generalization is always bottlenecked by the part that can least generalize, right? So in this case, we put very little robotics bias into it, and we didn't fine-tune the model. We didn't put any data into the model. We just leverage zero-shot performance, and we see pretty good generalization. Yeah, basically an even performance over all other distribution tasks. Cool. So that's the pivot work. As I mentioned, it shows some science of life that you can use visual prompting to help you to do robot manipulation, and it can help you to do spatial reasoning. But one thing that we found is that spatial reasoning is still an important weakness of vision language models where we want to improve. So I want to introduce this work called the Spatial VLM, Endowing Vision Language Models with Spatial Reasoning Capabilities. It is a paper in the CVPR. It's going to be presented in Thursday morning, I think. So feel free to check it out. Spatial reasoning is a central capability. A lot of your activities of daily living involve spatial reasoning. For example, you bought a new furniture and you want to place it in your house, or you want to squeeze through a tiny gap, like human can do this effortlessly. However, the best multimodal large language models still struggle with it. If you ask it binary predicates, for example, is something on top of something, is something below something, on the left to the right. If you ask about metric distance, if you ask about anything metric, then the vision language model will struggle. Yeah, so we benchmarked a few state-of-the-art vision language models, and we find in some of the hard cases, we basically crafted a very difficult spatial reasoning benchmark, and we find some of the performance of vision language model is close to random, so it's not super good. How do we address this issue? Well, we can change the architecture of the model so it is more amenable to spatial reasoning, or we can change the data. In this case, we propose to improve the data that is used to train vision language models, and we see if this is a fundamental limitation of vision language model or it is just a lack of data. And our research suggests that it is probably more just a lack of data. So one issue with current vision language model is that they have been trained on internet scale vision and language model, internet scale data. And a lot of data you see on the internet is more suitable for captioning, right? It's more semantic than geometrical. And we feel this is a limitation of how we choose data for training our vision language model. So what about if we scale up a data about spatial relationships? Can we get a vision language model that can reason about spatial relationships? We want to do make the model understand 3D better, and we also want the model to understand metrics, right? We want to understand metric distances. And if we can get a model with spatial reasoning, and then we can also leverage the other reasoning capability of the large language model or vision language model by themselves. Basically, we can cross-pollinate different type of capabilities, right? The vision language already do some sort of math, and if the perception can understand distances, then we can provide these two capabilities together.
For the remote audience, there's some echo.
Do
you mind
muting
yourself?
yourself? Thanks. Cool. So how do we improve the spatial reasoning through data generation? We created a data synthesis pipeline that starts from internet scale images. And then we first run semantic filtering to filter relevant images. Not all images. We cannot do spatial reasoning on all images. For example, the stock photos of a product or a painting, it's very hard to do spatial reasoning on that. So we use semantic filtering to filter relevant images. And then we run a list of vision experts. For example, region captioning, region proposal, localization, metric distance estimation, coordinate colonialization like ground detection, and then determine what is the up direction for the image. And finally, segmentation. And then we can create a rich 3D context where you have a semantic point cloud for each of the region. And you can get bounding boxes, for example, you can get captions. And And then we synthesize questions. We synthesize questions about binary predicates, or we synthesize questions about sizes, distances, all sorts of questions. Here are a list of example question and answers. For qualitative questions, it's mainly binary predicates like behind, in front, or left or right. And for quantitative question and answer, those are mainly measuring distances or measuring sizes. And when we fine-tune our model on this type of generated data, we find the spatial reasoning performance increases. And when we compare with the other base model that haven't been fine-tuned on our data, we find our model performs the best. And not only for quantitative question answering, but also for metric distance estimation. So previously, we didn't know if if you train a vision language model, it is autoregressive decoding. Can it actually generate the numbers accurately? And we find, yeah, it can generate the numbers reasonably well, and even without any regression. And we can also use the spatial reasoning VLM as a reward annotator for robotics. In this case, we ask the model to annotate what is the distance between the Coke can and the gripper fingers. It is a very fine-grained distance estimation task. And as you can see, the estimated value is close to the quite close to the ground truth value, apart from the end when there is maybe occlusion or it's getting super close, goes beyond maybe the resolution of VIT. So we can use this vision language model. It has a language interface. You can use it as a general purpose reward annotator to guide the robot to do exploration. And it is very useful for robotics. There are some, we are very encouraged to see there are some concurrent works that build on top of our lines of work, or even do some parts better than our work. We're very encouraged to see that. One of the work is a spatial RGPT, which is grounded spatial reasoning in vision language models. They use the different sets of vision experts, but they follow the same recipe of generating data and then fine-tune a vision language model. One thing I think they did better is they didn't solve the object reference. So they reference by region. Reference by name is inherently noisy and hard, and I feel it's compounding a lot of different errors, but the referencing by region allows them to do even more accurate metric understanding. They're not just the concurrent work of this spatial VLM, but there are some interesting work that is concurrent with the pivot, which is built on top of the annotating images, visual prompting idea. And people have been using it for open vocabulary robot manipulation. And just yesterday, another work is released. It's called RoboPoint, which use a point set as a primitive for spatial reasoning. They basically fine-tune a vision language model that can output a set of points. So it is also very useful for the robotics domain. All right, so as we have established, we can improve the performance of vision language models through supervised fine-tuning. We can craft some sort of data and use 3D vision experts to generate data, and then a general vision language model can absorb those vision experts and just do better spatial reasoning. But we have also seen that the precision of this method is still limited. We want to see if vision language model or large language model can improve themselves through interaction with users. So, which is also built on top of in-context learning, right? When you are interacting with a model, you can teach it to do this, not to do that, and the model can learn things in context. We propose this work called Learning to Learn Faster from Human Feedback with Language Model Predictive Control. So this is a collaboration with many colleagues in Google DeepMind. There are two types of learning. Even for human, there are two types of learning. And for large models, there's also two types of learning. One, we call it day cycle, where we do in-context learning. The agent or the model need to perform some functionality. So you're teaching the model you are correcting the errors on the spot, and you can iterate with the model until it outputs the correct answer. Just like how you use ChatGPT or Gemini to write a piece of code, you will run the code and give it the error, and the model iterate on the code until it is correct. So this is in context learning. And at night, you can fine tune the models to just output better results, right? This is what we call in-weight learning. There are some evidence showing that in-weight learning generalize better beyond the training examples. And we want to figure out if this is true, or in-weight learning, does it improve teachability for the model? So we find that we can adapt the model both in context and also in weight. And there are some certain advantages of in-weight learning. And we found a recipe to improve the model, and not only improve model, but improve the teachability of the model, where it follows human instruction or human feedback better. So here's a motivating example. We were teaching a robot dog to do a high five. And every time, well, this is built on my previous work called Language to Reward. It generated a piece of code, which is a reward code, and then we run the optimizer, MJPC, to get a motion. So as the first motion isn't super good, and as you can see, it's not quite a high five, but its elbow touched the ground, so we can further correct it, right? Now we have a list of corrections, and finally, it is getting good, trending towards the right direction. We're teaching the model to tilt the other way, tilting toward the right, and lifting the left paw. And finally, we call it a success. However, we don't want to teach the model every time. It's quite cumbersome that you have to carry out such a conversation to arrive at the correct answer. So we just want to, and also language model has limited the context window. The more you teach, the more you're filling the context window, and you don't have enough tokens to keep teaching it. So can language models remember what was taught and learn faster in the future? So this is a fine-tuned model. Ideally, so this is our goal, right? And I'm going to tell you how we achieve that. So ideally, you just, next time, you just tell it to give me a high five and the left paw, and it just need 2 chat turns instead of 4. It can give the right piece of code. So first, we collect robot teaching data with non-experts. We created a ChatGPT-like interface, but for roboticists, right? So you can chat with a model. In this case, we use a Palm 2 model that we hosted internally, and you can chat with a model. The model will generate code, and there is a simulator interface. You can press a button called Run in Simulator, and the robot will run your piece of code, and you can observe what the robot does and give it a thumbs up or thumbs down. So we asked our robot operators to operate on this interface and collected a bunch of teaching demos. So throughout the teaching session, the robot will do something hilarious or it will fail. But eventually, like usually after if you are patient enough, you can guide the robot to do the right thing. So in this case, they want to teach the robot to sit, and it seems the robot is able to do that. We ran some statistical analysis on the collected data. So every round, the user can do thumbs up or thumbs down. And finally, there is a session success or session failed. So usually success sessions are shorter, right? Usually you get success in a few iterations. And if the iteration is super long, usually the user just get frustrated and then close the session and say the robot cannot do it. And average number of chat turns is negatively correlated with task success rate, and good rating rate per interaction. Good rating rate is positively correlated with task success rate. So this means the data we collected is quite meaningful. Then we basically fine-tune a language model. There are 2 ways that you can fine-tune it. So first, you can just fine-tune the model to always output the correct answer. This way, you skip all the reasoning process, and you basically teach the model, directly give me the correct answer, no matter what, the human kind of teach it in the middle. Or we could use the entire trace. We could use the entire trace as training example, right? We could teach the model to model human users. And when we teach a model to model human users, then you can do something quite interesting during inference time, because you can model human users and you can also model the human good rating or bad rating, right? You can run some sort of beam search and search in this space. And we find LMPC is quite effective. So on training tasks, if you just do, the first method we called LMPC skip, where you directly predict the answer. We find on training tasks, it works quite well. It outperforms LMPC rollout, where you model the user. But for test tasks, we find LMPC rollout outperforms LMPC skip. So modeling the user is helpful for you to generalize. You can view this as you are teaching the language model to listen to human feedback better. Essentially, it's learning to be a better code editing model, right? And we find this to be super helpful. Here are some numbers that we showed in the paper. We found that LMPC rollout outperforms LMPC skip in test tasks. But for one turn success rate, LMPC skip is better. And on real world examples, we also find the same. Like the LMPC skip outperforms LMPC rollout outperforms LMPC direct. And here are some tasks that we can teach the model to do. For example, we can teach a model in simulation close a door. We can also teach a robot to do a downward dog, which is a yoga pose, to hop happily. We can teach bimanual KUKA setup here without a gripper to do non-prehensile manipulation to position objects quite precisely, even with very small objects. We can teach a model to do the insertion of a plug. We can also teach the robot to move the apple to the block without knocking over the can. So it respects your constraints. And finally, we can do this in real world as well. I want to just quickly show a couple examples. So before teaching, if we ask the model to pick up the Coke can upright, it will do anything but picking up the Coke can upright. It will pick up the Coke can, but not upright. So in some cases, it will spill the Coke. But if we teach it and we say this is a constraint, it will then respect the constraint. Another task, which is pick up the left Coke can without knocking over the right Coke can, right? So this is super hard task. But we find after teaching, it is able to do the task quite well. Respect your constraints, model the world, all within the same framework. I want to show maybe one more teaching examples where we teach the robot to do a downward dog in the real world as well. Yeah, for more details, please take a look at our paper. So that's roughly what I want to cover today. We are exploring the frontier of vision language model and robotics. We find that we can mine existing signals for action generation related signals from vision language model. We can have targeted improvements for certain areas of capabilities through fine tuning. We can also just teach the model to listen to human feedback better so that the model can self-improve through deployment. If you want to build on top of our work, we open sourced in the work that I present today. I think we open source the code, and there are some data sets that you can use as well. Special thanks to the Google DeepMind Robotics team. I have collaborated with the team for a long time, and stay tuned for more in the future. Thank you so much.
Questions?
Thanks for the lecture. I wonder if you do code the process end to end, how you debug like failure case, or this is from perception errors or like control errors or something.
Yeah, that's a super good question. I guess you could also predict, apart from the action generation, you can predict some structured representation as the intermediate output, right? Chain of thought, for example, help you to debug how language model works. And I guess in robotics models, you can also do things similar to chain of thought, where you can ask it to generate intermediate output.
which interpret representation do you usually use for the debugging?
That's a good question. We haven't settled on one representation yet, but looking at the progress of robotics, for example, 6D pose have been a very useful representation, or proprioception information have been a very useful representation. So I guess people could start with those, right? Another thing is that although we are working on the era of foundation models, we shouldn't just throw away what more traditions, like for example, state estimation, planning pipeline, those work, right? We should rather incorporate that together with our current progress.
In the end term, do you also consider like object cost estimation, like 6D cost estimation for inference, like for training?
Not right now, but we might be interested in that direction.
Thank you.
The other thing, for hands-on manipulation learnings, there are two streams, like one is for using the diffusion policy for trying to optimize the alpha losses, while here most of the work done by PDMs uses like the VLADR-based next token prediction. And we know that one is more robust to noises and the other is more generalized or to like with the common sense knowledge. How do you think these two works should go in future and merge or even consolidate, or how could they work better for low level nodes?
Yeah, that's a super good question. So I guess you are referring to in one end, like for example, diffusion policy is super robust and doesn't generalize super well. And for action token prediction, they generalize reasonably well, but it cannot do quite dexterous tasks. I guess we are trying to get the best of both worlds, but it's a research problem. It's an open problem. How do you combine the two recipes together? I guess one naive way is to take pieces from each recipe and try to combine them. It's not super clear. Like, for example, diffusion policy, there's no good evidence that it can generalize, but it's a super interesting open research problem that people should work on.
How much do you, when you're running inference of the large models, is it how impractical do you think that is for making like commercial product with it?
Yeah, that's a super good question. I guess there are different level of reasoning you need to do for different tasks. For manipulation tasks, if it is simple, usually you don't need a huge model, right? For RT1, I think it's 130 million parameters. And for RT2, we have like from 10 billion to 55 billion parameters. The more number of parameters allow you to generalize better. The fewer parameters, you can run it at a faster frequency from 3 Hertz to 10 Hertz. So it's eventually a trade-off. And with the people working on quantization or acceleration of these models, I don't think it's that impractical. I think one day, and a lot of people working on device acceleration. So I think one day we'll be able to run a fairly large model that can do generalization reasonably well in a domain, and we can deploy them on real robots.
Hi, my name is Rita. Thank you so much for an awesome talk. I work in human interaction and language governance. I've been using SAFe and RD1 and have some open source. I had a question related to the language to robot translator. It looked like the examples that you were showing, they're very, the constraints should be true always, like most to the right. Can you talk more about what are your thoughts if the constraints are more temporal and long horizon, like don't do this until this is achieved? So what are your thoughts or insights on how to handle that? Thank you so much.
Yeah, that's a super good question. I think that comes from a modeling assumption from language to reward, because in language to reward, we assume the reward function is not varying. It's not a function of time. So one way to do it is to have like binary predicates, and that can trigger, for example, a new reward. We have experimented with that but with mixed success. Also, teaching a language model to understand temporal is also reasonably hard. So we have tried something like that, but I think the solution might be you have a time varying reward function. It might be a good solution for it.
Hey, cool work on everything. For the pivot model, you talked about how like the different sizes of Gemini models, like would improve performance based off of RLHF style feedback. Yeah, exactly, right? You have the A, B, C, D. Is that like a linear relationship? Like is A like 100, 200, 300, or is it like a million, a billion, a trillion, right? Like I was curious if it's a linear relationship or you think it's like an exponential one?
It's more like a exponential one. Yeah. And the Y performance, you should also take it with a grain of salt because this is 2D cosine similarity. How does that translate to eventual task success rate is not super clear, but it's positively correlated. That's the best of our estimation.
Cool, thank you. So one last question, James.
Hi, I'm Maria, and I work on visual language models. I'm curious to understand a bit more, about chain of thought. Do you think that it is easier to generate good explanations in language, or is it easier to generate good actions directly from vision? And if so, what do you think the impact of chain of thought can be in like robotics?
Yeah, that's a super good question. I guess I've been like, so I'm also an author of the chain of thought paper. So for chain of thought, I think for the robotics domain is quite interesting because if you collapse the chain of thought to text, then it's inherently semantic, right? So it kind of limits your generalization ability. In RT2, we mostly do the semantic generalization. But I imagine a world where you can do chain of thought in other modalities. You can do chain of thought in probably more geometrical representations. And that way, I think it's more amenable to the field of robotics.
Thank you.
Wow. Do you think that language and image data is enough to learn this fine-grained control, or does the robot need to experience it itself?
Yeah, that's a good question. I guess so far we are working with whatever it is on the internet data, and I guess there will be more and more robotics data like uploaded to the internet as well. RTX is one example. So I think the robot need to experience itself. Like for example, here we are seeing maybe there's a performance ceiling. That is because we have just a limited amount of people talking about robots or like robot videos on the internet. The moment that we have more kind of first-hand data, robot first person view data on the internet, the scaling performance will be different. And by scaling the model that I showed in one of the slides, I also mean we jointly scale model and data. It's not just model size.
Let's thank our speaker again, and thank you so much for
Okay. Sorry. All right, this is a view from the classic autonomous driving system. And the Wave is building the next generation, which we call it the AV 2.0, which is an end-to-end approach, which means we have a single neural network that models the driving problem. So you see, like we just have a single neural network to replace all these different modules. And of course, we will have some safety guardrail to ensure that our driving plan from the single neural network is safe and feasible. So this approach, this is a data-driven approach apparently, so which means that it scales with data. So that means the more data you feed it into, the better driving performance it can have. Also, this is a very generalizable framework, which means like if you have data from 2 different countries or different vehicles, it can generalize on the driving ability and make the driving even better across these 2 different environments. And lastly, this is more human-like driving because you don't have to define this driving rules by hand engineering. So all these driving rules are learned by data. So here you can see some of the very complex driving scenarios, such as like overtaking packed buses, navigating through roads and roadworks, and also driving in the snow weather, although it never seen such environments, and also nudging into the traffic for unprotected right turns, which all this just driving by a single neural network. So how is that possible without this any rules? So we kind of look at the end-to-end neural network by visualization of the attention mask. So we surprisingly found out that although we never define any single rules, the rules can be learned from the data. You see this nice emergence of the rules on the traffic light by looking at the attention. These are all scenarios of starting when the traffic light turns green. You see it's looking at the traffic light until it turns green, and then it shifts the focus on the road ahead. This is like very similar to human behavior because when we are stopping for traffic light, we usually sometimes look at the traffic light and say, if it turns green, we will look at the road ahead to move forward. So this gives us a lot of confidence that we don't need any rules. All these rules should be learned by data. And this is also a driving clip in the autonomous mode for AV 2.0 driver. And you see that this is like a very complex scenario, but it's also the typical driving scenario in central London. You see a lot of giving away to cars. We have set cameras, but I'm not showing here. It's also trying to negotiating of merging into the main road. All this done by the single neural network. And of course, you will see lots of like edge cases, such as here's a car reversing, and our car can correctly deal with these scenarios. And for other scenarios, such as avoiding a bin, and also a cyclist passing by, it's all doing this maneuvers safely and efficiently in a more human-like manner. And it also generalized from day to night, as I just mentioned, that we only need a small amount of night data to enable the generalization to the night. And yeah, Wave has been doing this end-to-end approach for several years. And the last year was a remarkable year because we saw both industry and academia shifting to this kind of end-to-end solutions, especially the Tesla FSD Beta V12 announced they use the single neural network end-to-end training for this driving, replacing over 300K lines of C++ code, which is a great sign for the end-to-end approach. And also from the academia, we saw UniAD, which is a modular end-to-end autonomous driving framework, won the CVPR best paper. But of course, there are still many challenges. So I'm going to show this some of the challenges that we figure out throughout this research during these years. So the first one is very apparently the explainability problem. Because we use a single neural network, it's really hard to know what's going on in the neural network. For the traditional stack AV 1.0, you can look at these bounding boxes or predictions and looking at the if-else rules to figure out what was going on. But for a single neural network, it's really hard to debug and figure out of the explainability. Secondly, so end-to-end neural network are not good at high-level planning and prediction because it's usually operating on frame level. So it lacks a high-level context or the memory to know what's the current phrase. And so the challenge part would be how can we add memory to the end-to-end neural network, and how do we improve the common sense reasoning and prediction, and how to add or change the rules without retraining the single neural network. And the third challenge is like end-to-end neural network. It's scalable, but it requires lots of data, especially when there are some edge cases, such as the edge cases that happens one of 1 million scenarios, such as you have a reflective car in front, and also such as some rare objects, such as a giraffe walking on the road. You may never see this in your life, but sometimes it happens. And also sometimes people are being very creative, try to follow the self-driving cars. And I believe some of you might see this funny clip. A man is wearing a stop sign shirt, trying to follow one of the self-driving cars. And it works. So our solution, and also the main topic I'm going to present today, is to learning the basic principles of the word by using vision and language. So for vision, we want to train our single neural network on cheap unsupervised video data so that we can learn how the word operates, especially the physics of the word. And for the language part, we want to train a model on the internet scale text data, or we can leverage the pre-trained large language model. And this is for learning the common sense reasoning from the human world. So I'm going to talk about each of these topics. So first, let's get into the vision, which the topic I'm going to present today is the generative world model that Wave is currently working on. So let's first imagine, and if you see this image, and you can probably predict what's going on next. And actually, human is very good at this. You may think that we might be giving way for the white vehicle to merge in, or it's actually we're kind of going around the white vehicle. So humans, it's very good at predicting what's going to happen next. And how did human acquire this knowledge? So it's basically since very early age, human observe, interact, and learn from their environment, such as human can learn by observing the car drives on road rather than flying. So we have this prior knowledge that the car usually drives on road. And also we learn by interacting with the environment. If we bump into any objects, we feel the pain, so we will try to avoid that next time. So especially machine learning models should also learn this physics or the model of the world in a similar way by observing the videos, by interacting with the simulators, or by observing other objects interacting with the real environments. So Wave is investing this world model for autonomous driving from very early days. In 2018, we already published this paper. We are learning to drive from a world model. And we also have some research on the future prediction of the other instance and from this bird's eye view. And last year, we have this paper of trying to leverage the world model in imitation learning context. So last year, we also announced this Gaia, which is an image level world model, which means that we are able to predict what's going on in the future a few seconds from a single image input or a video input. We did this by using a VQ GAN with autoregressive transformer and also the diffusion model to make the image looks nicer. We also have this condition on video on different modality, also with text and also with action as input so that you can control the future prediction. We train this on thousands of hours of wave data collection. So here's some clips showing that the emergent behavior of our Gaia model, which you can see that if we sample different tokens, that we can generate different futures given the same video context. And also you can see there, we can also have very nice multimodality interactions, such as the same car. If we sample differently, the car can be giving way for us, or we are yielding to the right car and let them merge in. So we also show that our Gaia model is not just interpolating between the frames, it's actually learning a true world model. So by prompting the model with some auto-distribution actions, such as you're trying to crash into that car, which we never had such data in our training data. But we actually can imagine what's going on with such behavior. So we also have the text as condition. So that means you can also generate video conditioned on the text. So you can use all your imagination, controlling the weather, or control the time of the day. And we saw Gaia model is able to generate this plausible videos on your conditions. We're also able to generate minutes of plausible driving videos by keep doing this autoregressive generation. So you see that with even minutes of generation, we are still able to clip on the driving distribution. And you can also simulate any scenario you want by giving it action or language. Such as here, we gave it a language we're 15 minutes behind the bus and the action to accelerate right. It can generate this very nice video. So our latest work, we extended that with controllability of the dynamic agents by adding this bounding box condition. You see that this bounding box is our input to the Gaia model, and the Gaia model can generate very nice video condition on these bounding boxes. And this can unlock a lot of potential of generating edge cases or auto-distribution videos and adversarial scenarios. So the opportunity ahead of Gaia is we can integrate Gaia into Wave's on-road driving AI so that our driving model can understand the future and can predict the future, which can make it driving safer and more efficiently. And we're also going to extend that into multiple view and multiple sensor generation. And we can also use Gaia to train and also to evaluate our driving model. So the second part I want to talk about is language-mediated driving. Because vision and language are two most common modalities on the internet, and also two major modalities that human perceives. Let's first look at why we need language in driving. Because if you look at the traditional rule-based self-driving stack, it's usually for interpretability, you have to look at these bounding boxes or if else rules. And with regard to long tail scenarios, it's usually not robust to auto distribution scenarios. And also it's not scalable as you have to do this pre-mapping of each map. And also when scale to different countries, you have to define different rules. And if you use a large language model into driving, you can actually ask a question to the driver and to say why it generates this action. And for the long tail scenarios, you can have this zero-shot reasoning ability or in-context learning for better reasoning and long tail scenario ability. And for scalability, it's because LLM was pre-trained on internet scale language data. So it has the knowledge from the whole internet. So that means like you can generate to different countries, even with zero shot by prompting the model with your different country. We had a proof of concept early last year, by using a simulator or simulator output the state of the world with different vectors, such as the route, the vehicle, pedestrian, and your ego states. And we ground these different states into a large language model by using pre-training. And then we also output the action from the text modality, and we use that to drive in the simulation. So how do we achieve this? For most importantly is data. We generate a pseudo vector caption data by creating this language description of your vector states. And then for the driving QA data, we use our expert large language model to self-generate question and answer data. And the training has two-stage training. So for pre-training stage, we pre-align the vector states with language space by supervising this pseudo caption label. And for fine-tuning, we fine-tune on the QA data. I'm not going to show very many figures here, but the result we got is like the large language model can improve on a lot of metrics comparing to the model without large language model. And the pre-training stage boosts the performance. And our evaluation also shows that the GPT-based grading tend to be very forgiving compared to human grading. So here are lots of qualitative results, but the most important point is that we can ask this large language model any question about driving, such as some perception questions, like what's your how far is the closest car? Are you able to crash into it? This is kind of very out of distribution question, and the large language model is figured out this closest car is 12 meters away, and we are not going to crash it into it. However, this is just a toy example and a proof of concept. The most importantly is how do we incorporate a large language model into real-world driving, and how do we align with human intentions rather than extrapolation from ChatGPT or some human annotators. We presented our work, Lingo One, which is a fully grounded video question answering model. We use a BLIP2 inspired architecture And we did a lot of ablation on the video fusion strategy. And the late fusion strategy works best for us. And in our tech report, we also released 3 different data sets. The most importantly is action data set because it's very it's collected from our human driver who is trying to comment on their intention while driving. So this is very important because it contains a lot of intention of the human drivers, rather than just by guessing of the intention through the labeling process after the driving. For benchmark, the language is very hard to evaluate because there are like so many different phrases. So in this tech report, we kind of have a novel approach by using a learned metric. We train this LLM judge by giving this a lot of this good question and bad question and also human scores so that we can learn to output a score of how good is your answer in the driving context. And our lingo model is able to do commentary and also visual question answering. You can find all these videos on our blog on our website. But the main point I'm going to talk about is like we also extend this work to referral segmentation, which means it's able to output a different modality, which is a segmentation map. This also helps us to ground the question answer on an object level to prevent hallucination or other problems. However, this is just like a video commenting model. It just has vision and language. Of course, we also want action. So we proposed our VLADR model early this year. We call it Lingo 2. It's fully grounded vision language action model. The architecture, again, is very simple. We just have different modalities, different encoders, and then we add the driving action as the output. But the most importantly is to have this data, the language kind of connect to the vision and the driving part. So here's a video showing that we actually deployed this VLADR model into our vehicle. So what you see here, the trajectory is outputted by the VLADR model. You can see it's also commenting about the communication, about the intention. Here's another video. You see that it's saying its intention, switching lane to stay on the planned route before it's even doing that. So that shows that our VLADR model is trying to leverage the language modality for this reasoning task. And then our action is fully grounded on the language part. We also tested the language action alignment on our in-house nerve simulator. You see that with the dynamic agent and without dynamic agent, it's actually trying to say the different language, such as with the pedestrian on the crossing, is saying that stopping for pedestrian on zebra crossing. And without that, it says accelerating to the speed limits. And that's also aligns with your action if you look at the graph of the speed. So with this architecture, we are also able to control the vehicle with language. This is really the next level of self-driving cars. If we prop our VLADR model with turning left and turning right, it can generate different actions driving in our simulator. And similarly, if we prompt it with stop behind the bus and overtake the bus, it will generate different actions. So we really want to unlock in the embodied AI at a scale with a foundation model, which is not limiting to the vision or language modality. So we want to focus on the next generation of foundation models, which we can have different modality of inputs. It's not limiting to image or text. By using a lot of different public datasets or closed datasets, we want to train our model that can generalize on a lot of different inputs and then adapt to these different inputs. And for output, we also don't only want it to output action or language. We also want it to output any modality that we want, such as perception, simulation, or a lot of different embodied AI applications, such as like a robotics task. So to summarize, so today we talked about different ways to achieve autonomous driving. So for AV 8.0, especially the rule-based driving model, it's usually composed with perception, planning, prediction, and edge map. So it's not robust to auto-distribution problem. It's also not scalable. And when it comes to AV 2.0, if we naively use a data-driven end-to-end approach, that would require a lot of data, unlimited data to cover all the edge cases. If we go to the principle-based autonomous driving stack, which contains the end-to-end apparently, and also we have a world model to imagine the future. We have a vision language action model that can do the reasoning through the language modality, and also powered by the foundation model that's pre-trained on a lot of different inputs and outputs. So we got the benefit of the knowledge from the whole internet, and we understand the real world physics, how the object moves, and we can predict the movements. And it also have very nice zero-shot generalization ability. And we can also use some of the tricks in the large language model, such as the chain of thought reasoning, to improve the reasoning ability. And Wave is pioneering the principle-based autonomous driving to make it safer and smarter. And the principle-based learning, supercharging AV 2.0 and foundation model will help unlock the full potential of the intelligence robots. So with this, this will be the end of the talk. So if you're passionate about self-driving, and so please join us to keep this interesting journey on the AV 2.0. Thank you.
Any questions?
Thanks for the great talk. This is Michael Whale. Two questions. And one is how will you deploy all the foundation models to the onboard to the car, and do you deploy all of them to the car, or do you deploy part of them, you deploy in the car? And the second is about the evaluation. With all end-to-end model, and if you want to evaluate the model with integration, you need to kind of run the end-to-end installation in your evaluation instead of kind of evaluating different models of the driving unit. Thanks.
Yes, thank you for the question. So specifically for the vision language action model we showed in the video, we actually deployed the large language model on board because we used a small language model, not large language model, but that's also kind of pre-trained on language data. And the most important latency is from the sample of the tokens. So if you sample smartly, like just sample a few tokens, or just try to not sample too many text tokens, you're able to run it in a kind of relatively fast manner that's able to use that for drive. And for the second question, for evaluation, it's indeed a very important problem and also a very hard problem to evaluate the AV 2.0 stack, because You have the image as the input, so you can't simulate this like bounding boxes and do this evaluation. But we have some work on the neural simulator that can simulate very real real world images by leveraging the neural simulators, such as a nerve or Gaussian splatting that we can use to evaluate the AV 2.0 framework. Yeah. Thank you very much. Thank you.
Thank you very much, Tom. I just have one question. Trying to get the intuition for why the language is as necessary for an autonomous vehicle. I can understand in some interactive setting where you maybe have a robot you're interacting with, you want to tell it to do something, and you say verbally and process that. Before an autonomous vehicle, thinking about it, it should be monitoring its environment visually to decide what to do. So I'm wondering why the language element is being brought in for the autonomous driving specifically.
Yeah, that's a great question. So interaction with robots is definitely a very large part of large motivation of using large language model for driving. But more importantly, we think that the large language model has some emergent behavior of zero-shot generalization, and also some of the reasoning ability emerged with large language model by doing pre-training on this internet scale text data, which contains a lot of coding or high-quality textbook that really train the reasoning ability. So by leveraging this large language model, so we believe that it makes it better to handle auto-distribution scenarios because this educates us everywhere in the world, and our driving model need to be smart and really human-like to understand this like a zero-shot generalization to this auto-distribution scenarios, so that we can make the driving model safer and more efficiently. That's the main motivation of using large language model for driving.
The end-to-end solution seems like very scalable. I'm just curious, how do you handle faulty sensors in such a setup?
How to handle
faulty sensors? So
okay.
What if the sensors are starting to behave, incorrect?
Yeah. So so currently we are using very lean sensors. So currently on our vehicle, we just leverage the camera. And but I imagine in the future, so if we want to scale this model, we will definitely involve many different sensors such as radar or like microphone. You can hear the sound of surroundings. And I also talked about the foundation model, which is pre-trained on different modality inputs, not only with image, but also with sound or with other vector inputs. So hopefully it can understand this degradation on one sensor, on one camera, or on one type of sensors, and then try to leverage the other sensors to driving, such as like if we are driving a car, if it can't suddenly we can't see because of fog or something, we will try to listen, try to use other sensors to drive safely. So I think our driving model would, our future driving model should be able to have this ability to deal with this degradation of sensors.
I'm just thinking, following traditional sensor fusion, where you actually have a state, so kind of thinking about hidden state or something like this, where you get the information from, whatever past and try to kind of leverage that. So kind of combining, these two worlds, like, the end-to-end, which is data-driven, and based on the traditional sensor fusion, so kind of embedding those structures. So this seems a little bit also kind of, well, it seems like another direction, kind of.
Yeah, it's kind of similar direction, but it's just like different implementations. Because what we really want to build is just a single intelligence model that is able to handle this this sensor degradation or other cases without the implicit under engineering of all these cases.
Thank you. I'm wondering, we see things like chain of thought, a language model can be capable of
reasoning coherently, autoregressively, but still be able to make incorrect initial conclusions. In the same way, how can you verify that the actions predicted from your model are actually grounded in the reasoning that it outputs?
Yeah, that's a great question. That's actually also a very important question because usually saying is one thing, but doing is another thing. I think it's the same for human. It's also the same for the large language model. It's really when you ask some question, so it says like one thing in the first, but another thing in the end. So I guess this is still an open research question. So how to improve this alignment between text modality or the alignment between text and the action modality? That probably we need more data for this alignment, or probably we need some new laws in training this model to penalize the disalignment.
Thank you. So one last question.
Yeah, as you roll out new models in order to improve on the existing model, how do you make sure the new model is better? What kind of metrics do you use? And did you maybe have occasions where you got better in certain areas but worse in other areas? And how does that work in practice?
So for evaluation, we have offline evaluation and online evaluation. So apparently the golden metric would be the online evaluation. So we have a fleet that we test for our new models. So whenever we have a very promising model that has the best performance on the offline evaluation, we will do this online evaluation. So we will do this evaluation on kind of a very large quantity of evaluation that we are able to make a conclusion that it's statistically better than the previous version of model. So yeah, so in summary, it's a very tricky problem to know which model is better, and we use the final metric, which is the driving performance on the road as a golden metric.
All right, let's thank our speaker again, and thank you so much.
Thank you.
briefly on the topic of robot EXP action condition scene graph. Scene graph while interactive exploration for robotic manipulation.
Yeah. Hi, everyone. This is Yunzhu. I'm very excited to be here to talk about our oral papers like Robot EXP, action condition scene graph while interactive exploration for robotic manipulations. So this is a work like in collaboration also with my students as well as with some Amazon folks. And he already attribute to the first author, Han Xiao. He has been doing an amazing job carrying this work over. So this work is actually lies in those categories of how we can use and leverage foundation models to allow the robot to do better physical interactions with the environments. We all know that foundation model has been amazing in providing some higher level understanding of the environments. So for specifically this work, we want to leverage foundation model to allow the robot to have better high level modeling of the environments, specifically at understanding the scene's structures and how we can allow the robot to do better explorations and be able to memorize what it has seen through its interactions with the environments. In order to memorize what has happened and what are the objects inside these environments, there has been a thing that people actually used in the field of robotics, which is scene graphs. Scene graph describes a spatial relationship between different objects inside these environments. There has been some very interesting work from Luca Calon's group, and also this concept graphs has also been quite interesting in injecting foundation models. But all of those works missing one very important piece, which is action. In all of this existing work, there'll be a robots just constantly moving around inside these environments, making passive observations of what's around this object. It doesn't actively interact with these environments, which actually is quite important if we really want to put the robots in our home environments. For example, looking at this bottom left image, you realize if we want to put the robot in our home, trying to do something useful, like preparing the meal or set up the table, you have to first understand where all the ingredients are, where all the condiments are, before you can do something useful. Or on the right, like videos, this is a video clip from Tom and Jerry. You realize they are trying to looking for something, but they are not doing this kind of exploration in a random fashion. They identify what objects require explorations and then understand what type of interactions should be in place in order to interact with that specific objects. Then after the interactions, we'll have to memorize what we have explored and be able to use those type of information for the downstream tasks. So in this specific work, we developed these robotic systems that will be able to explore the environments, understanding how and what object requires explorations, and memorize the information for the robot to do downstream tasks. Here is a very simple example. Given this tabletop environments, there will be like refrigerators and some kind of cabinets inside this table. And the robot will first realize, okay, those are the objects that might require exploration. The robot will first observe the environment, build some type of scene graph shown on the top left, describing the action conditioned relationship between the entities inside this environment. For example, if you want to retrieve the can, you actually have to open the refrigerator to get the can. And if you want to retrieve these condiments, you also have to open this like drawers in order to get to that condiments. So after robots observe the environments and explore the environments, it will be able to build this high-level understandings about this action condition relationship of the objects inside its environment. Then the robot could be able to use this type of information to do downstream tasks. For example, retrieve the object and be able to set up the table. This action condition scene graph precisely describes if you want to retrieve a specific object, what type of action you should do in order to get this Coke can in order to place it in the right location. After the robot set up the table, actually this task is not finished. The task specification actually asks the robots to also place a spoon on the left side of this place. And the robot will be able to like going through this scene graph and realize there isn't a spoon inside this scene graph. So the robot will say, okay, I need help. So there will be a person coming in and place the spoons on the left side of the plate. So be able to build this type of explicit representations of this action condition relationship of this environment, the robot will be able to understand how to retrieve objects and do downstream tasks. The general pipeline works like this. Given this setup, the robots will first obtain multi-view RGBD observation of the environments. And we will pass them through some open vocabulary object detectors and be able to fuse those informations into our memory module. This memory module contains both high-level information, like this action condition scene graph. It also contains like low-level informations that describe the geometry as well as semantics of this information for the robot to plan its behavior to open drawers and doors. And those information will be fed into large foundational model to tell the robots what nodes can be further expanded and what type of behaviors can be used to further expand that node. And then the robot will be able to execute those actions and be able to obtain new observations from the environment in order to do this perception, memory, and action loop. So given this type of like exploration systems, we mainly test our systems in 3 different types of scenarios: obstruction, recursive reasoning, and some intervention scenarios. For the obstruction one, first, the robots want to explore all the objects inside this environment. But for the robot to open the door of this cabinet, of this white cabinet, there will be like some type of condiments obstructing the robots. The robot will be able to build this scene graph in a way that understands if you want to open the left door of this white cabinet, you have to first move the condiments away before you can explore what's inside. So those type of action condition relationship in resolving the obstructions of this environment has also been encoded in our scene graph representations. And after the robots explored these environments, we are showing some kind of visualizations of what we get in terms of low-level memory. Here, the top left is our original observations. On the left, we will be able to identify what are the objects inside these environments. And we will like iteratively click different objects. And you'll be able to see that there are objects actually hidden inside the cabinets that will be able to be stored in our memories and for the robot to retrieve that object if that object is relevant for the downstream task. After this obstruction case, another example will be recursive reasoning. Here, we are actually facing this nested dough. And the robot, after it's explored the first layer, to realize, oh, there might be additional layers, it had to do further explorations. So the robot will do recursive like explorations to build this very, very deep graph to understand like those are actually nested objects that has objects within other objects. And based on this kind of nested scene graph, the robot will also be able to like recover it into its original states. This really shows that our system can do real-time and reactive explorations of these environments. The third one is to show that our system is robust to external disturbance. Here, after the robot first explore the environment, it will first open the right side of the white cabinets and then open the left side. On the left side, there is actually an orange inside this cabinets. And then there'll be a person comes in, like remove the orange from this environment. The robots will know those regions has to be labeled as uncertain and you have to explore those regions again. When the person places a cocaine on the right side, the robot will also realize, okay, the right side of this cabinet has to be labeled as uncertain and be able to do this subsequent explorations. And currently, we are trying to extending this type of systems into larger scale home environments. Here, I'm just showing some preliminary results showing that we can like build this both high-level memories in the form of scene graph and also low-level memory in the form of geometry and semantics, describing some like household environments. Here's another case. And we have also done some very preliminary initial studies on having a mobile robots trying to work inside those environments and be able to explore the objects that requires explorations inside these environments. For example, there's 2 drawers inside this environments. After the robot opens the top drawers, it will find an apples inside these drawers and be able to label that inside our scene graph. Here's another example where the robots realize it actually have to lift up the clothes in order to review the objects underneath this clothes and then be able to place this clothes back to recover its original state. So to summarize a little bit, so this work is really about how we can leverage the foundation model's high-level reasoning capability to help the robot build these high-level understandings of these environments. Specifically, we leverage structures in the form of action conditioned 3D scene graphs. And the foundation models help the robots identify what objects require exploration, how to explore those objects, and memorize what it has seen. And you can also see it as the other way around, where we leverage robot behaviors to augment the foundation models with the tools in the form of these high-level and low-level memories that supports complicated downstream tasks. And as soon as we release this work, there has been a lot of interest from, especially from the industries. People from Amazon and from Boston Dynamics AI Institutes has really also reached out to me to see if this type of systems can be deployed in a wider and larger range of systems to really build this action condition memory of larger scale environments. So if you are interested, I'm happy to talk about any like interesting questions and subsequent steps that you want to chat about. That'll be all. Thank you. Happy to take any questions. That's a very good question. So for this specific case, first, we are not really stress testing, not stressing the advances on the robot's low-level behavior capabilities. So a lot of those low-level behavior are somewhat semi-hard-coded in a sense that, for example, if you want the robot to open the drawers or doors, we actually will detect where the handle is, understand the local geometries, and be able to do some principal component analysis of the normal directions, and will specify the grasping locations as well as pulling directions. So a lot of those low-level like action behaviors are actually somewhat hard-coded. So in order to, like, for example, really extending this type of system to more in the wide and more complicated real-world environments, handling all different kind of variations of handles, deformable objects, and cabinets. So in some of those scenarios, a lot of investigation has to be in place to really enhance the system's low-level interaction capabilities. And our lab has been doing a lot of work on deformable object manipulations, like those granular objects, fluids, ropes, etc. Those type of behavior can actually be integrated in this work. It's just we didn't get the chance to do it because this work is really highlighting the high-level understanding and modeling capabilities. Thanks.
Great talk, thank you. I wonder if you've been benchmarking this with like retrieval-based methods or other like using methods using language models.
Yeah, this is a very good point. So first, in terms of the concrete benchmarks, because we have these explicit memories, so we have compared with method that doesn't use those explicit memories. As you can imagine, you'll constantly like forget it has explored that doors and explore that door again and again for many, many times and just loop over there. So that's not very ideal. So by having this explicit understanding, some structural understanding of this environment, again, this is our design of the scene graph. There could be all different kind of design of the scene graph. Both can be both explicit and can be implicit. It's just for our specific scenarios, we find that this is very good at helping the robots understand, okay, this region has been explored, or this region has been perturbed, it had to be further explored. So this explicit memory has been very, very helpful, especially compared with like just query the foundation models on what to do next. So this is a first type of comparison. And the second type of comparison is that in this work, we use GPT-4. We have also compared with other open source like vision language model to see if they are equally powerful. What we found is that given this benchmark, given this framework, we can do like plug and play of other foundation model. It can still do something reasonable. But still, like from our experiences, like GPT-4 still performs the best. Mm-hmm. Yeah, thank you for the questions. So if you look at this video, you'll be able to see like before the robot make any interactions, it will move around to observe the environments. And observations are actually RGBD observations. So because we know where the NA factor is in relation to the worlds and where the pose of this camera is in relation to the NA factor. So we'll be able to like do the camera calibrations and put those RGBD observations together to be able to build this kind of fused point clouds to representing our low-level geometric memory. Yes, those point cloud coming from RGBD camera. And we have point cloud, but point cloud obviously have noise. And in order to fuse them into a coherent space, for example, this object from this view has to be associated with the same object from a different view. So there has to be some kind of fusion in place in order to build this type of low-level memory. Thank you.
Everything all right? Yeah. Let's get started.
Okay. Thanks for waiting. My name is Chong Hao from Shanghai AI Lab and the University of Hong Kong. So today I'm going to present my work about Drive LM. So actually, this title is a little bit different from the paper title. It says towards language model in end-to-end autonomous driving. So yeah, let's get started. So briefly, I would like to give a brief introduction of what we think end-to-end driving looks like, at least so everybody will stay on the same page. So as you know, autonomous driving has many challenges, like we have various weather, illuminations, and complex scenarios. This will cause into many corner cases, or we'll call it a long-tail problem in either perception module or prediction module or any sub-module in current autonomous driving systems. So for now, basically, academic side and the research, academic side and the industrial side reach a balance that a common autonomous driving system can be decomposed into three parts: the perception, prediction, and planning part. The perception part is basically about asking the question like, what I want. This will require the model to do basically object detection or segmentation of the surrounding world to get a semantic understanding of what's the object or agents around the ego vehicle. Then when it goes to the prediction part, it will ask the question like, how will they go in the future? Here they are refers to the other agents, like how are the other vehicles or agents go in the futures? This we call as a prediction problem. And then finally, we go into the planning problem, which is the ego vehicle future trajectory prediction, usually in the representation of a waypoint in the future. So this will guide the ego vehicle, where should it go in the future. So for now, there are two main fashion to do such a system. One is we call as a classical approach. Another one is called the end-to-end paradigm. So the classical approach will formulate each task or each module as a individual models to do it. Like for the perception task, we have a detection model to handle it, and the output of this stage will be either bounding boxes or the mask of the point cloud. And this kind of output will direct the prediction module to do the future trajectory prediction of other agents. And finally, those kind of trajectory will be summarized and along with the bounding box as well to the planning module to generate or predict the ego vehicle's future trajectories. So on the otherwise, end-to-end paradigm are working in the same way, but for each module behind it, we have the gradient descent rather than the bounding box or the trajectory, those kind of, we call it human design patterns to pass the informations. So, sorry. So why we want to do an end-to-end way? Because we think that if a model take a raw set data as the input and produce a plan, and this kind of plan will really affect the low-level control and action as the output. This type of design, we can handle the corner case in an end-to-end way or more specifically a data-driven way. So in this way, all modules can be optimized at the same time through the gradient descent. You don't need to redesign your human design patterns in each stage so that the information might get accumulated errors
between each design. So sorry, I have spent a little more time on the end-to-end things because this is why we want to do end-to-end driving at the very beginning. Then during the 2023, we know that ChatGPT or vision language model got its change. So we want to ask a question: what if we put the vision language model in such a paradigm that we can have better generalization or better corner cases for solving ability to in the driving scenarios. So let's take a step out of the driving side and take a look at how the embodied AI people or the robotics people handle such cases with the vision language model. So I would say this is a general paradigm of their work. So usually they come with a chain of thought VQA task. Here the A will stand for answer or action, whatever it is. And then they will have a vision language model with a redesigned tokenizer. So this kind of tokenizer can directly map the text output back into the action space. Here, the action space is a discretized space of like a several numeric result that a robot arm can actually take action on. And then finally, a de-tokenized module will de-tokenize the action, a predicted token back into action. Then this kind of action could do the real robotic control. So why do we do this? Why they do this? Because they think that, okay, embodied AI is an open vocabulary field, and using language as control or language as description, the model can better understand or better fit into humans' daily life. And they hope by doing this that we could get a better generalization in such a paradigm. But they also raise two questions in this scenario. So first is that, okay, robotics are usually use language because they are usually facing open vocabulary scenarios, but driving is not. Driving is, you would say that 99% of scenarios are really common cases, like you see all the highways car or street cars. They are very common in the scenario, but only 1% that really matters to blocking us to going from L2 to L4. So is it the right way for driving people to open the language toolbox as does in the robotics people for the driving scenarios? So we think this is partially yes and no. So for the yes part, we think that for the generalization and interactability of the vision language model, this is very good ability that driving people would like to have for their system. And we are seeing that the vision language model are getting better and better. This is also giving us promising confidence that such a model can solve so-called corner cases or long tail problem. So yeah, that's our work at a glance. So basically what we do is just build a data set for perception, prediction, and planning. And we build a so-called graph of thoughting, a graph of reasoning part that we, for each type of question, you can either grab the nearly question or the further away question in the logical chain to form a graph structure to help you do better reasonings. So yes, so these are the data labeling system. So we actually ask the human labeler to label each scenarios to ensure that those VQA, those VQ pairs are actually annotated by human rather than a machine or GPT generated ones. And this is our agent. We would like to say that for the perception and prediction and planning, they do have a internal or inherited reasoning logic behind them. So we want to specifically model such a reasoning process by prompting techniques. And here are some results. So our initially finding would say that we can find that such a model training with a graph of thought thinking, we can have a better zero shot ability when the model is trained on nuisance and do the zero shot on Waymo. Yeah, and also there are some limitations, of course. So for now, vision language model couldn't really handle the driving specific inputs such as LiDAR, IMU, and so on. And also for the testing, we are still doing the open loop testing. Well, it is not favorable by the industrial side, so a closed loop planning might be required in the future. And also it is an old saying problem that if efficacy constraint that, okay, you can run a vision language model on cars, so how do we do the latency? So this kind of question, I think this will leave a very large research space for the research people, but also I think it is worth doing that because we can see the gains in some way.
And yeah, this is the one-page takeaway. So end-to-end autonomous driving, we want generalization and explainability, so we do driver IM to answer it. Thank you. And any question, welcome.